So that way you can share your summary.
So, okay. Can you hear me? Okay. So you can hear me fine. Those attending remote. Yes. So we have, okay, we still have a few minutes, 5 minutes. So I would like to get from you first, who or you are familiar with neural networks, deep learning? A bit, okay, a bit, okay. So first thing, this is a very introductory tutorial or workshop. So if you are a specialist on this, if you do this on a daily basis, this is not for you. This is really, really basic. And so we mentioned that from the very beginning, that this is not for specialists on the area, it's more for white people educated with academically capable. So we will not go into just the narrative, the history, blah, blah, blah. We will try to run actual neural networks, training some things, experimenting. So we will be using, hello. So running actual networks. So tell me, who among you are familiar with Python? So you consider sufficiently comfortable with Python. Okay, this is the idea. I divide this so you can attend what you want, what you need. So for this morning, we will be covering just a little bit generalities of neural networks, deep learning. So how those things work. After that, I will run another notebook showing with some experiments or some one classical problem, the handwritten digits, so to see how those things looks in practice. And after that, a couple of examples running pre-trained networks for some things that so could be interesting. But I'm not assuming at this point that you know to program, how to program in Python. So for those of you who are not from, well, both remote and in person, who are not familiar enough with Python, or let's say Python, you did something, but a few months ago, you don't remember very well, I will be running a 2-hour fast forward lesson on Python programming this afternoon. If you feel familiar with Python, if you know how to manipulate arrays, NumPy arrays, how to make slices, how to manipulate all those things, you can skip entirely afternoon session, because this afternoon we will not be talking about neural networks. We will just be leveling the field for everybody who are not familiar with Python. Some of you are more familiar with some other language, like R. So that is the idea. This afternoon, it will be entirely dedicated to Python from the very beginning, from variables to classes to NumPy arrays to all that So you reach to the point where you can understand how manipulate the boxes that this thing would be. For tomorrow, we will return in the morning again with neural networks, doing a little bit more stuff with them, basic. And in the afternoon, so I changed a little bit. In the afternoon, I will be making an introduction to machine learning. So for those of you who probably are not familiar with machine learning, can attend the afternoon for tomorrow, and in 2 hours we will be covering the generalities of machine learning. Those of you who are familiar with machine learning techniques, classification, clustering, all that, can skip entirely the afternoon session of tomorrow and just arrive for the next day to return to neural. So it will be something that I'm trying to fit for you, the different levels of skills, so everyone can attend what they really want to attend and can skip the other parts that are less interesting or just redundant for. Another thing is that I conceive this workshop a little bit in the same way as neural networks work. So neural networks work by repeating and reintroducing elements over and over. So what I'm doing is a little bit like that. I am mentioning neural networks, and a lot of concepts will seem, okay, looks fine, but the landscape looks fine, but I don't get the details. So after, I will be reiterating all that. So you will be seeing some things coming and re-entering here with a little bit more depth. So we will get the details of what is missing from the previous one, and after more elaborated things. So we will be going and re-going a little bit in the same fashion. So this one, for example, for today, I'm not assuming that you know the details, for example, of Python programming very precisely, but you are able to just see a little bit how those black boxes are doing things. So you will be doing those things with me, and you will be experimenting with them. Tomorrow, and this afternoon, we will be filling the Python gaps that you could eventually have. And tomorrow we will be entering again and seeing in more detail how those neural networks are created, why they work the way they work, and using that in practical cases with the 3 major deep learning frameworks that we use today. So today, basically, the market for those things have shrunk a little bit. So people, 95% of the people use TensorFlow, PyTorch, MXNet, and pretty much in that order. So everything else had somehow collapsed or attached to those big projects, supported for the most part for big tech companies. So that is what we will be doing. And I'm not attached to a single framework. I want to get the idea for you to see that those things work differently, but they are basically doing the same thing in different ways with different approaches that could fit better some cases, some industries, or some practicalities. But I don't want to feel attached, and you should not feel attached to one framework because those things change. If you concentrate too much in one thing, that thing will disappear. What should be with you is all the science, all the engineering that lies behind those things. Those things are the thing that really stay. The surface of that changes a lot. So you see that this thing has 10 years of success, basically. And on those 10 years, things have appeared and disappeared. Nobody of today talks about piano, cafe, those things were popular at some point, disappear. Now some things are popular today. In 5 years, maybe they are not. they will be not around. We will see. But for you, it's important to get this this view. So 3 frameworks. I will be using those 3 frameworks pretty much at the same percentage that they are used in the industry. So I will be concentrating for most part on TensorFlow, Keras, a little bit of PyTorch, so, and a little bit of MXNet. So you get a feeling of all those things. So perfect, 9 a.m. So I think we have, let's see. So we have around here 20 people around here. We have 43 online. And again, if you want, we were lucky today, and Kyle bring us some post strips. So I think we can, we will be sticking feeling the topology that I was expecting. So you will be sticking around the walls. And that will, I hope that will work for everybody. So this is not something, this is not a movie. This is not somewhere where you sit and you just relax and watch it. No, I want you to test those things on your computer. So the first thing that I want is that you go to this place. So you should get an account on Thornyflat by now. So we will be dedicating a few minutes to discuss how that works. So this is, and I will be, this is the website, and I will be, for those attending remotely, I will paste that on the chat. So that's the website, ondemand-tf.hpcwvu.edu. So the first thing that we will be doing is familiarizing a little bit with this environment. This is a web interface to our cluster, to one of our clusters, that is called Thornyflat. A cluster, for those who you who are not familiar with HPC, a cluster is basically an aggregate of computers that look like computers, but with some, basically like big refrigerators full of connected stack of things that with some lights that pop up. And all those computers are connected with a very special network interface. And they are there for serving many users, running many jobs or applications, in particular for a long period of time. So that's the purpose of an HPC cluster. And we have one that is very decent. And we have around 160 nodes, 60 or 170 nodes, maybe, with 40 cores per node. And so we have more than 3,000 cores there. We have machines with different amount of memory. For us, our definition of a small memory machine is a machine with 90 gigabytes of RAM. We have other machines with 180, 180, 360, and 760, something like that. So you see how those machines look like machines, but they are not like the laptop. They have many cores. Those cores are a little bit slower than the typical high-end computer, but they are too many. And we have a lot of memory, far more than you see typically on a machine. And in some of them, on some of those machines, we have devices called GPUs. Those are a specialized hardware. They are connected to those computers, so they can accelerate very specific kinds of tasks. Not everything, very specific things, typically linear algebra stuff. Matrix multiplications or vector matrix multiplications, they are very good at that thing. So that is And machine learning and deep learning, we are doing a lot of that. So that's why they are so good in doing what they do, GPUs. And we have like 20 or just around 20, a little bit more than that, maybe, GPUs on our cluster. So we don't have enough GPUs. So we have like 120 people attending. Right now we have around 20 people here, 40 people, 51, 55 online. So we don't have enough GPUs for everybody. The good thing is that I will show you how this works, and I prepare those things so you can run those with CPUs. So you can connect to the cluster and run that. You will get exactly the same if you use a GPU, but it will be taking, it will be 50, 60 times faster. It's just the difference is time. It's not the experience, it's not how the results, it's just how fast they can produce the results. And for some things that we will be running today, they are fine. They are super fast, so you can get this in a few minutes. For some of the things that we will be running on the third day, they will be taking a lot of time if you run those on CPUs. And so we will see how many people will get at the end. So at that moment, maybe some of you can execute things on the GPUs. So first thing, go to this website, on demand, HPC, go here, and you should be landing on something like this. You should be in a stage, something our dash, what we call a dashboard for Open on Demand. So this is just a web interface to our cluster. So what is running behind, what will be running behind, is happening on a remote machine. It's not running on your computer. Your computer is just front end for this thing. And let's start with this. So this offers a few things that could help us. One, and I'm just showing this for you just in case that we need something like this, is doing this, is opening a terminal. I will be, sir? Oh yes, I will be doing it. So here, so there are several things that you can do here. All of them are here on the top. So this is our door of entrance, a nice word of entrance to the cluster. And there are several things that we can do here. So I will be showing you one that could be intimidating for many of you. I will just be asking you to run this once. So let's see, it will be looks like this with a prompt there. Let me see if I can. I probably cannot make it bigger. So. Oh yeah. Okay. So it will be looking like this. So the first thing that I will be asking you is to copy the materials to your. Yes.
Whenever we try that, it appears to actually send like your connection to the server.
You are getting that?
Yes. Log off. Try log on again. Maybe once. When is the last time you logged on?
So first, land on this. And if you are getting problems, remotely, we have some colleagues of mine who are looking at the chat. My connection to your connection to remote server. Nate, do you know if something is happening with the VM?
Yeah, I refreshed it.
Now it works. So I'm getting something like that. Refresh. Oh yeah, they mentioned that. Refresh the page. It's working back again. So this, I hope everybody just mentioned this. This is important. So I'm dedicating a little bit of extra time to this because we will be using this area all the time. So this is important. So here, clusters, turning plan. This will be, oh, okay. I'm getting excited. So now I got a feeling with it. That's good. And I'm okay. Yeah, that's something that could happen because too many people searching for this. So what we'll be doing is copying the materials to your Scratch folder. So let's go back a minute. What you see here, when you execute commands here, is just the data, the files and folders that you have on a remote machine, on a cluster, on Turnitin. I prepared some materials for you so you can run this neural network on your own. All the data, so the training data, all those images and things that we'll be using are right here in this computer. But we just need to copy that to your own folder so you can run those and change the notebooks. So that's the first thing that we will be doing. Execute this command. Yes, sure. Making many types. And you should have a Scratch folder. Native, one of the system administrator create for all of you a symbolic link to a special folder that we have on the cluster. Scratch. That's different. Scratch. So this is one way of copying all that data. I will be copying that data to a slightly different folder because I already have that other one. Screw that. So I will be copying.
They copy already. It's already in the lab.
No, but it's with a typo. So I noticed that Nate did a typo. So let me see if I. Well, for you it will be like this. So what I copied there are so the notebooks that we will be running. So all the Python codes that will run those neural networks that we'll be learning, and the data. The data here are very classical examples. Well, I was not expecting this. Let's see. This is just big and we will not be using this. Yes, you can execute that. Well, that's the advantage of that command that I will be showing you again in a minute. I am deleting some folder there that is big and they have a lot of images for random people, Schwarzenegger. I will not be using that. So yeah, so still the folder is big. By the way, there are ways for you to take all this data back to your own computer. You can run those by your own. So if you want to know more about how to operate with the cluster, I suggest in the meantime talks. Here, this is our documentation page for our cluster. If you go here and you want to see the instructions about not here, about transferring files, one alternative is to use Globus. This is what I'm using here on my computer to transfer the data from my computer to the cluster, and it's the same procedure that you can use to transfer the data from the cluster to your own computer if you want to keep all this with you, the notebooks, the materials. As far as I know, yeah.
Guillermo, in the online, they are using the Scratch DL. You should correct that.
They can use that if they want. They don't need to do that. Let's see. I can try to assume that they will be using that. I will be using that. See. Okay. In the meantime, let's explore. Let's see. Let me delete that. Otherwise, it will take a lot of time for me to do. Some other things that we can do on this. Go here to interactive apps and click here where it says Jupyter Notebook. See how basically. No, the answer is no. They should be still working on the terminal, on the tab. If you jump to another tab, so it will be. The only restriction with this terminal is that it lasts for a couple of minutes for security reasons. So if you just let this terminal open there in a couple of minutes, it will shut it off. Right? So yeah. So let me see if I got. Yes. Question? Yeah.
You should download all the packages.
Yeah, I will go to the command again, so you can copy. I just checking that. Okay, it's 4.6 gigabytes. What I have there, and 274 files. So this is manageable. Let's go here and let me show again what we need to execute. Ideally, do it like this. Do it like this. And so I will be copying and pasting this. So everyone should be on the same page. So I copied that on the chat. And so for you, something that I hope you can see there on the top, be careful about this. There's some subtleness, subtlety of here of our sync. There is a difference between putting a dash, a slash, or not with this command.
Guillermo, some people is complaining on the chat, and I think the problem that they have is that the AV minus AV have to have a space, and also the same.
So let's see.
The space is not.
There is a space here. The command is rsync. There is a space here. There is a dash, a minus, AV, and this is important. All the things needs to be in the same case. In the Unix is very strict with those things. And computers are not intelligent, so they will not understand what you want to do. You want to tell them exactly what you want to do. Here is another space, and here is a path for a folder. This is how paths looks like on Linux Unix machines. They start with a dash or dash, the slash, share, tutorials, deep, underscore. So this is not a space, this is an underscore, this is underscore learning. Yeah, okay. I'm sorry?
I couldn't connect to the step that he says. Connection amount.
Oh, you have to.
You have to try again because after 2 minutes it will kill due to security reasons. When you open a terminal,
You can just keep
try
the
that.
return key, and that will keep that video alive.
There is someone behind you. Okay.
Not anymore.
Okay.
I'm just gonna start with that. Thank you.
Okay. So anybody, anyone who had trouble copying the data, it was okay. You got it okay? Yeah. Yeah. Okay. Or you're trying. Okay. Try. Let's go slow. Let's go step by step because we are in a hurry. Yes.
What's the difference between using the /dl?
Oh, yes, that is important. In this command, rc, if you put a dash, it will copy the contents of the deep learning folder. If you put it without the dash, it will be copying, starting, including the folder deep learning. So that's the difference. If you see without with the dash, it will be just leave you a set of folders on your scratch. Will still continue to work, but it will pollute a little bit your environment with a lot of folders. So it's better to keep this without the slash. So you get a folder that will just contain this and it's fairly organized. So you see, I guess. Password. In my case, because I already have this, I'm just using an extra folder just. And another advantage, another thing of this command. This command, is, let's say, idempotent. If you use it again, nothing happens because it will check that all the files that are on the destination folder are already there. So it will not waste time trying to copy something that is there. It's just checking the files and the timestamps, so the sizes of those files. So if the file is there, if they have the same size and it has been modified exactly the same time, which is the same file, it will not copy that again. So this is a nice command. This is just the only command that you will be executing here. Everything else will be inside a Python, Jupyter Notebook. So that is the only thing. And eventually, if I find something, I will be tomorrow asking you to refresh this or get a new copy of the data, just in case. So again, typically, if you don't execute anything on this terminal for a couple of minutes, it will be terminated, and you just open a new one. No problem. So this is one thing that you can do here. I will be leaving this. And so this one crash.
Can I make a couple assumptions while you're
Yes.
going back up? So did you get into like the HPCs and like on-demand? Like,
Yes, that is the, yeah, that is the first thing, is going to this folder here that you see here on the left. So I'm trying to get into that. So that is the first thing. Can you see that?
Yeah, like I suppose like a 2020 vision, but I still have like latency and load. I
Okay.
suppose.
Yeah.
Write that on the chalkboard.
Yes, sir?
We want to write the URL on the chalkboard so it's bigger for people to see.
Well, not, okay.
No, they didn't give us time.
Yes, okay. If you can do that for me.
Yeah.
Thank you, sir. Spell.
Okay. So this is the, so now you have the data, and now we will start on interact with it. So click here on demand, yeah. And click here on Jupyter Notebook.
Is that readable to everybody?
Yeah, that's so much helpful.
So, and somebody who didn't got the data, could you raise your hand if you didn't got the data? It's okay. So, and I will be trying to execute this on the simplest way possible, at least for today, using just CPUs. Go here, you click here. This is what we did if you lost it. Interactive apps, Jupyter Notebook, and you land on this form to fill. This form is asking you a few questions about what you want, which are your requirements for the job. Those are interactive jobs, so they will give you a computer for you to run things up to 4 hours, and with a certain amount of resources that we can ask. So here I will be using the latest version of Python that I have, with the latest version of, or a very recent version of GCC. And I will be changing this to a standby. So try this one. Wall time, let's say 4 hours. So we can run a few things here. And number of cores, let's see. Let's put just 2 cores. The thing that we'll be running for today will be very, let's say, narrative. Maybe I will change this a little bit for when we start showing pre-trained networks. But 2 cores, so everybody will get a job running really quickly. 2 cores, no GPUs for this. This queue is like those places in the supermarket where you go and there is one for elderly, for pregnant women, so there are countries who are careful with that, even more than the United States. There are places where you can go if you are just buying just less than 10 things, 10 items, so a fast queue. And there are some others where people arrive with a big car. So, so you know, with that, okay, I have this number of things. Okay, should I go to this one where we have 1 person, but they have a ton of things on that car? Or should I go to this queue where there are 5 people, but they just carrying a couple of things that will be, so this queue will move faster. That is the same idea on this cluster. Again, we have 160, 170 machines behind this with 40 cores. So we have more than 4,000 cores, and we typically run 50 or 60 people are running things at the same time on the entire cluster. So this is something that's a resource for many people. It tries to be fair for everybody to use them. And one of the ways to hold that fairness is for you to select the kind of resources that you want. So let's select a standby. Standby is with a limit of 4 hours. So I will be using that limit. 2 cores. So I know that we have 40, but I would just need 2 for the kind of things that we'll be doing. No GPUs. This queue doesn't offer GPUs at all. You can skip this, forget about this, Jupyter, and hit launch. So let me see, probably will go on. Let me recapitulate until this changes. CPython 3.10, select that one. Stamp the queue, select the standby. Hours, I select 4. You can select a couple of hours. You can get a new session if you want. 2 cores for 1 machine, 2 cores on that machine. 0 GPUs, not additional modules, nothing. I will be running Jupyter. Typically, it's very fast, but we have 65 here, 20 here. We have like 85 people hitting the machine at the same time. So it will be taking a little bit more time. Okay, just in case this is taking a little bit for you, we can start listening to me and keep an eye on the screen so you get this. When this thing executes, when you will be landing on something like this. This is the dashboard for Jupyter. You will be seeing this scratch folder. This is a symbolic link to a folder, and you will be having a folder like this, deep learning. Inside that folder, deep learning, there is a folder called notebooks, and we will be running this first notebook here. This is what I have here already prepared just in case that this is taking too long. Yes, so you will be seeing, it took me a while, but this is what you see. You will be seeing something like this for the jobs. No singularity image. So let me see, with a question from there. So, yeah, you can skip that entirely, the singularity image. Because we will not be using that for this exercise. Tomorrow and the third day, yes, we will be using the singularity image, specialized or optimized for one of the 3 frameworks that we will be using. So if you select something like this selection of singularity image takes no role, is entirely skipped. It only works if you execute this selection here, running Python via singularity image. Singularity is a containerization solution. For those of you who are familiar with containerization, it's like Docker's containers, but it's specialized for HPC, for high performance computing, for clusters, where some security policies typically will not be fitting well for the way Docker's works. So Singularity is that solution. But we will be not using Singularity here. We will be selecting Python 3.10 here. And when you run, you land on something like this. So something like this first. You go into a little bit low here, Scratch. and here deep learning, notebooks, and you select the first one, chapter 1A, deep learning, and you land here. I hope you can get to this point. On this network, in this notebook, there is nothing to run, but in the second, third, and fourth, they will be using this morning if we can. Otherwise, we will move some of the pre-training for tomorrow. Yes, you will be running those things, and you will be executing and changing and experimenting. This is the idea of the workshop, that you experiment in things. Again, this is not a movie. So I will be skipping this, and we will start discussing what deep learning is. Deep learning is a subsection of something bigger that is called machine learning. And machine learning is just a subset, a portion of something bigger that is called artificial intelligence. Artificial intelligence is an area of computer science devoted with creating programs or techniques that allow computers to realize tasks that we typically associate with intelligence behavior, with intellectual activities. It's not about making machines sentient, so they're giving conscience to a machine. That's science fiction. Probably happens, maybe not, but this is not science. This is not what we are talking about. We are talking about making computers to do activities that we typically delegate to a human brain or a brain. In that big area, there is a subset that is called machine learning. That is the purpose of the objective of that area is to create models that can produce results based on data, learn from examples, rather than a programmer thinking about the solution for that problem and going into the computer code and writing that from the beginning to the end. That is the difference. When you know the solution, you can go and type that on a computer, an algorithm that will take that, and no matter which input you offer, you will know what it should get. That is, let's say, the traditional way of thinking with this. But now we are trying to think about how we can take examples, how we can take things that we know what should offer and use them to create a model. And inside that, there is deep learning, which is basically neural networks, and we will see how there are two ways of approaching this. Yeah. It's breaking me the image. Okay, at least one. Okay. So for that, basically we need three conditions. It's good data, a lot of data, that the data offers some patterns. So there is something that we can search on the data. And the lack of a good mathematical model or explanation or theory behind it. So we can solve that, let's say, with an algorithm, with an equation. If you have an equation for that, why bother? Use the equation. If you don't have too much data, we will be restricted a lot. There are techniques to take advantage of a lack of data. But the good thing is that, and the reason why deep learning grows so much is because we are basically drowning in data today. especially data that is generated by humans, but also data that we collect with sensors, with satellites. And all that richness of data is just feeding data centers, storage, terabytes of data, and we can use that data to create models that work with it. Learning from data is something that is, if you think about it, it's something that is natural for a scientist. So there are two ways of approaching science. One is that you have an intuition and some principles, some mathematical guiding principles, and you develop a theory on how the universe, how the world should work. And after, with observations, you can get those observations, astronomical observations, for example, or by doing experiments, you can see if your model, if your theory works or not. Also, you can do predictions, and you test those predictions, and if those predictions were correct, your theory gets ground, it becomes stronger. If those predictions start being weaker or have issues, well, you start thinking that the theory is good, not so good, or it's something that we should replace for something else. I just bring this example here to notice one case in the history of science. This is Kepler. And he basically took observations himself, and with the help of one guy who would have some difficulties, was like a party guy and very rich. Tycho Brahe. And they got data about observation of the sky, and they were trying to get that data. And he was starting working for a model for the observations of the sky. You see, when you see the sky, when you see the planets do things that are very weird. So you see a planet going this way, and it will go back, and it will continue. What the hell is this planet is doing? What the hell this celestial object is doing in the sky, going in one direction, going back, and moving? Well, you try to find a model for it. Yeah, you can think, okay, maybe, well, the first model uses the air, which looks naturally, it is the center of the world. We are the center of the universe. Well, everything should move around us. So create a models, and we use the simplest model is everything should be circles, should be spheres, because it's the most perfect figure for us. So we try with that thing. But this guy was trying to think about something else. Maybe that model was not good enough, and it was evident that was not good enough because it was not capable to detecting the sweeping of this movement of those objects, the planets that were different from the stars. And he developed a model based on data, was trying to fit the data with different figures. We tried circle, and the circle didn't work. With the next one, he put, imagine that he put an ellipsoid. Well, it didn't work, but it almost worked. So maybe he tried, well, maybe we put the center of the ellipsoid in one of the foci of the ellipsoid. So you see the ellipsoid is like this. I'm sorry for those, I think that we are not. Let me see. The video works. I don't know if it works. So they have something here. Those are the so you can put here nail, here put on a nail. If you want to make an ellipsoid, you put in the string here, and you can go here and draw ellipsoid. So he put the planet here, or he put the sun here. Put the sun here, and he said, okay, so, okay, the planet is here, and we are also another planet running this. So that could explain why this is doing like this. This is one thing. And also, he didn't know calculus. It was Newton who created calculus. So he was just thinking in a very different situation. He realized that this area here, for a certain amount of time, is exactly the same with the area that the planet moves in the sky is the same with the same amount of time. One of the group. All that based on data. So they took data, he created a model, he rejected the model, put another model until the data fit. So that idea, they fit it with the data. And also, he took the data and he have like a training data. This is the data that I know, the data, the position of the stars during the last 10, 20 years, the planet, sorry, during the last 20 years. And he has that data. But he could keep the data from the most recent year or two to see if the data was fitting what was expecting. And after that, he can predict things. Okay, the planet should be here at that moment. And even better, and that's what they are mentioning here in those tables, when we got alignments or when we got eclipses. The eclipses were important at that moment in time. Those things were associated with good and bad things. So people pay attention with eclipses. And if you can predict that, it's because your model have predictability. You can take that model and apply it to the future and know what the model will produce. So those tables are very famous. So you see a lot of data here. This is the output of that, the Tabulam Rudolphi. So you see here. And this is, from the scientific point of view, the origins, one of the origins of learning from data. But here is the human learning from the data, meaning from the observations. With deep learning, we are doing pretty much the same. We have all the same ideas here. We have data. We have a portion of the data that we use to train the model. We have a portion of the data that we use to see if the model is good or not. We have data, again, also more refined to improve details of the model. We make predictions with that data. And the predictions could improve, and we get better models, and people think about it. Something more than that. Notice that this is the model that we have for how the planets, for Kepler, is that the sun is in one of the foci of the ellipsoid, and the planets are turning on those ellipsoids. But for us, what we see is different because we are one of those planets. We are turning the sun. So we need to transform our point of view. We need to transform the way we see the world to this model. There are transformations to the data. And this is exactly what deep learning is doing, transforming the data in ways that are non-trivial, that are very convoluted. We will be demystifying all that, but this is what is happening. It's transformation to the data. We will see that with a nice examples. Now, let's go again to deep learning. So we explore what machine learning, learning from the data is. Let's go back and see deep learning. Okay, there are two ways to approach in deep learning. One is the biological approach. Oh, yeah. If they can see this?
Yeah.
Okay. I will try to be attached to this corner of it. So there are two ways of approaching deep learning. Deep learning and neural networks are, for us, terms interchangeable, so we use those as the same thing. So one way is to think about biological neural networks. Keep in mind that those are just approaches. Don't feel attached to those ideas for too long, because at some point you will be escaping from the science and entering into the science fiction and the magical world. And if you stretch too much this kind of idea. So one is that neurons, they have special cells with a lot of tentacles. They are linked to each other. Those tentacles, they're called axons, and they have dendrites, they have some terminals, and with those terminals, they connect to other neurons, and they fire, they make a signal. Those signals, well, are like electrical signals that are happening with some molecules in the middle that are switching, and the next neuron could take that switch, do nothing, or take the switch and fire. So that is like a cascade that is happening in our brains in very convoluted ways. That is one thing that could suggest us to eventually use something like that to do operations. This is the biological approach to that. That biological approach works up to some point, for example, for the eye, because we have like a front neuron that is there, just behind in our retina. Just the terminal that is receiving the signals from the cones, from those special cells that are photosensitive, and they are firing and sending the signal back to the brain, here in the middle, in front, a little bit back, where they will be processing the image. They will be taking and relating the image that we see. So there is this idea of moving from the front to the back. In the entire brain, this idea of front and back is not so clear. So that's enough. The other approach is approach from computer science, from mathematics, where you have functions. This is a function, you see here. It's a function. We will see the details. I know that we have, for you, some of you, you are familiar with this, with those terms. Some of you are undergrads online, maybe. So I will be trying to move back and forth into the math, so nobody get lost in those. So we have some inputs here. So those W0, W1, W2 are just numbers, 3 numbers. We get three numbers. And we are making an operation. This symbol here is a summatory, it's a sum. So we have 3 terms in that sum, and we are doing the simplest function that we can imagine. That is just taking the 3 numbers, multiplying those by some 3 numbers that we have inside this cell body, and with those numbers, we are multiplying them, taking an extra number, doing something else at the end, and returning the result in the output. Yes, to switch the data. Opening the Opens notebook. Home. So do you? So here for that. So do you are here? Can you go to the Scratch folder? Yeah.
Oh no, it always initializes me in my home directory.
Okay. But are you able to
There
go?
should be a symlink in your home directory to your stash.
Oh, okay.
In the files tab that you put.
Yeah. It's because without that same link from Open on Demand, you are not able to see the Scratch. But you are familiar with that. You are a long-time user, so that's why I don't know if you have it. But for everybody else, we create, Nate create those same links. So like a shortcut, so a link from the home folder to the Scratch, so people can store stuff. And the reason why I'm not asking you to put the folder, this deep learning folder on your home folder is because we have 10 gigabytes there. We are a limit of 10 gigabytes on the home folder. The folder for all the data is 5 gigabytes, but let's say 80% of you did not have an account on Tornit before, so you are new, so you are fine. But we have like 20% of the people who are already HPC users of our cluster. So they maybe have something there, 6 gigabytes of data. I will ask them to put 5 terabytes. You get fully the quota there, and it will be a nightmare to tell, okay, you need to remove this, you need to remove that. So that's why I asked you to move to the scratch. So, okay, this is the first thing. So one, again, biological idea, neurons, moving around, connected to each other. Another idea is the perceptron. We have a function like this, a very simple function with some inputs. So you have 3 values as the input, and this function produces an output. And we can use this function for making what in machine learning is classified. So we have dots here under some distribution. One typical case is distinguishing cat and dogs. So we can take the weight and the height, and we have a few parameters for them. We have a few parameters for something else, for the cats and for the dogs. We spread that and we ask, okay, we need a model to distinguish a dog from a cat, just from those parameters. So there will be spreading those variables. So this will be a 2-dimensional problem. So we capture just 2 data from the dogs and cats, the weight, the height, and that. And we are trying to classify it. We are trying to make a function that is capable to distinguishing one from the other. There will be trying with different lines of separation. Just like that, this is a simple thing, just draw a line. But maybe there is a better way to make that line. This is, for example, the technique that we use with something that we will discuss tomorrow in the afternoon, for those who are not familiar with machine learning, that are called support vector machines. So it's just a way for deciding a reasonable line that we can draw to separate those sets, basically taking some support vectors, so some location, and trying to make an avenue in those points that is as wide as possible. So we're trying to make a nice road that we can separate the data. Well, another option to solve that problem is using things like this. And we will be executing one perceptron, and we will be training the perceptron from the beginning to the end. We will see how this works tomorrow, I think. And those things work nicely when things are simple, when you can put those lines. But there are cases where that doesn't work so well. So that is where it comes, the idea of neural networks. It's a little bit like this, functions, or think about this like neurons that are receiving some input and finding some output. But this time, we are putting more layers. We are making this just bigger, more complex. We are putting some inputs. We are putting some neurons in the middle that receives the inputs. And after, well, this is a simple, non-deep neural network. So we have what we call a hidden layer. So we see the input, we see the output. In the middle, we have some functions happening in the middle that contain some state that will be doing the operations, but they are not visible. This is like a black box for us in the middle. Well, the idea of deep learning is taking this and making a stack of hidden layers.
May I ask a question?
Yes.
That may or may not make sense, but we can probably shape it. When building these network architecture, do you use like the sequential or do you actually use like class-based when building this?
This is something that we will discuss, let's say tomorrow, or this is the building, how you build them. This, in this case, is something that you can solve with the sequential, for example. The traditional sequential, for example, in TensorFlow, we have a network, a layer, and after a layer, and after a layer. There are some others that doesn't fit that idea so simple. So they jump, they connect, they jump, they have ways of connecting in non-trivial ways. So that sequential, you need to abandon that and move into something different. That's connected. So, but this is what we're thinking is that the simplest thing that we're introducing is just those dense layers. This is called a dense neural network. So dense because everything is connected with everything, but in a sequence, in layers. So you have an input. This input send those inputs and numbers. There's nothing. It's just a number. Inside this circle here is just a number. Inside this circle here is a number with some parameters that will weight the inputs. We'll take those inputs, we'll do some operations that we will discuss in a moment, and produce an output. That output will become the number that will be used for the next, and after for the next, and after for the next, until you get an output. You get something at the end, the output. Okay, so in practice, you have an input layer, some input, some layers in the middle, some output, and that output is the product of your function. So you can think what happens in the middle is a black box for now. You have an input, you get an output. That is something that is a function. For the cases that we are doing, this is a deterministic function. So we are talking about deterministic neural networks here. So if you present the same input, you always receive the same output. Those are classical in the sense that they use they are using classical mechanics. They're not doing anything beyond that. It's just function that if you get the same input, it will produce the same output, and the output is deterministic. And now, what we want is that this function have internal parameters that do what we want to do. So the trick is to tweak the internal parameters of that object, of that. And they have many parameters to tweak. So let's see another approach, another example here that is illustrative. This is coming from this blog. By the way, I put in, when I found something interesting, I put the sources. So you see on the notebook, they have links, so you can explore more. And I will give you a review of literature that you can use. So this is a very nice example with something very simple. You have this curve here. And you are asked with the task, okay, I need something that separates those two curves. Okay, the first model, again, like Kepler, which is the simplest model. Oh, well, the simplest model is draw a line. I draw a line, but what happens? The line will always cut this here, the second image. If you draw a line, you always cut that thing. So there are a portion of the blue line that will be in the red region. There is a portion of the red line that will be in the blue region. Okay, another way of doing this is, okay, what is the next thing after a line? Well, a parabola. We can draw a parabola and we succeed. But we need to know that we want to use a parabola here. It will be nice to have something that learns from the data and give us a good result. Well, this is a very simple example of a neural network that is not deep. They have one hidden layer, so they have this layer in the middle is what is called the hidden layer. This layer here is just the input that could be the X and Y locations of these red and blue lines. And here we have an output that could be just 0 and 1, or just something that says how much reddish that point in the curve should be, how bluish that thing should be. So it could be just one number saying the probability of being blue or non-blue means red. And what the network is doing is twisting the space, is making transformations to the data. A little bit like Kepler might have to do transformations to the observations to put them into an ellipsoid or for making the predictions. The network is twisting that in such a way that by rotating, stretching, deforming the space with some operations, you get a nice separation between the blue region and the red region in such a way that you can take a cut and say, okay, this is the red region, this is the blue region. This is what neural networks are doing. And something like this. This is another way, nice to see what the kind of transformations that a neural network is doing. You see here the functions. So the function is take the inputs, multiply by some internal state of the neuron, summing a parameter, summing a number, another number. So W, I, and B's are numbers internal to the neuron. The X are the inputs. And after that, you surround that with another function that is nonlinear. And what you do is a combination. This multiplication of W's and X. So everything that is inside the circle is what is called an affine transformation, something that is like a rotation, and skewing, and a scale. No more than that. Yeah? An affine transformation. It's affine or affine? I don't know in French if it's affine. So operations that you do with linear algebra. And after that, you surround that with a nonlinear function. That is what you see here. So you are seeing here on the first, here, look. Yes, here. You are doing rotations, the space. And at some point, what you will see are scalings and also the non-linearity. Those curves, when things become curved, is the operation of this non-linear function. That is the crucial ingredient for making these networks do amazing things, the non-linearity of that. So we start with rotations, scalings, skewings, and finally we are doing with the function, the deformations, the non-linear. This is another couple of examples, visual examples of what a neural network is doing. So you see here at the very beginning, you have like a spiral. And the spiral, the neural network, this very simple network, something like this, very, very simple, is taking that, is rotating, is stretching, is screwing that until you get something that you can cut and say, okay, we have a red region here and we have a blue region here. Perfect. But here we have something that this neural network, we haven't again in a spiral, but this spiral was a little bit more twisty, and this network was not capable of separating that. It will try, but this network is not complex enough to do the transformations needed to separate that. And now imagine that you have something like this. See here, it's another example that I don't have. Beyond those transformations, there is another thing that those neural networks are doing, is that they are playing with dimensions. They are adding or removing dimensions. So you see things from a different perspective. Imagine that you have here some red region, and you have here a blue region. Okay, try to separate that with a line. Well, with a line, forget it. No matter which line you throw here, it will not happen. Throw to a neural network like this, well, okay, we'll start twisting that thing one way, right? It will not be fixing that. But what about if we add more dimensions to this? So we put this in 2D, and now you imagine that we have 3 dimensions, you put more dimensions to this, and you take this central region here, and you push that region out of the plane here. At that moment, all that you have to do is cut, and you get it. So that idea, so again, transformations, they are very simple mathematically, just multiplying, and after another function that will include a nonlinearity, and also the possibility of making this with multiple dimensions, increasing the dimensionality of that, adding the capability of expressing this in a way where it's clear how you can separate that. That is another thing that those neural networks are doing. So now, this is the basic architecture. Yes, question? Yeah. Yeah.
I'm kind of new to the overview of that concept, but I think like each one of those nodes represents a function. I think generally.
Yeah, a function like this. Yes.
Sigmoid function.
Yes, we will see just in a minute. Do it.
Oh, sorry about that. I was going to ask. I know as you add more layers, you're going to like expand on the dimensionality of it. What's the theory behind the trade-off of just adding a different layer versus like adding the changing the complexity of each node?
We will see. I mean, in the next notebook, I think one nice example where we see that bigger is not better, deeper is not better, and a little bit like the answering the question about the complexity and sizing of networks, what they mean. By the way, when you said the dimensionality is not coming from the deepness here, the dimensionality is coming from the number of points here that I'm putting in one layer. So imagine that you see here, for example, on this one, we are taking something that is 3-dimensional. So you are getting an input, 3-dimensional. We are inserting that into a hidden layer, and the hidden layer is 4-dimensional. That, and at the end of that the hidden layer, we have 4 inputs. From the point of view of the output, we are receiving 4 inputs. It's a 4-dimensional thing. And now we are producing a 2-dimensional. So we are also reducing dimensionality at the end. So we are enlarging dimensionality is the number of nodes that we are putting here. What we get when we put more layers is making more transformations to the data. More transformation. Yeah. You want to complete?
No.
No, yes, no. Correct.
So going straight down is the number of dimensions and everything.
The dimensionality of the graph. Yeah.
There's like the hidden ones. There's this way is non-linear.
No, in the horizontal way are the transformations that are taking place. For how you will see that clear in the context of visual things, how they are capturing patterns from the data. For this kind of networks, we are just getting some transformations to the data. The data will contain data that it got from all the inputs collected and produce a result. And that they are collecting more of all that data and making another transformation. So it could be something like this 4-dimensional, and you are just exploding that to a 10 dimensions. And after you from 10 dimensions, if you can imagine it, you can think in 10 dimensions. Thinking in 4 dimensions is a little bit difficult, but it's possible after a while. After a little bit of courses in physics, you can see in 4 dimensions, but beyond that is a little bit difficult. You can think, okay, jump into 10 dimensions, and the world in 10 dimensions looks clean. And I can see that this region is this and this region is that. It was not clean when you saw that in 3 dimensions, or when you saw that in 2 dimensions. For the world in 2 dimensions, things could be harder. The dimensionality help you to make separations. And though dimensionality is coming from the number of neurons that you're introducing here. And the complexity of these transformations are the deepness somehow. But we will see that with examples, those things will become clear. So yeah, so in terminology on input layer, hidden layer, in this case we have just one. Yes?
So we can say that the neural network is a part of unsupervised machine learning.
Sorry?
The neural network is a part of unsupervised machine learning, or it's different?
No, it could be for all it could be used for all categories of machine learning that you can think of, like supervised, unsupervised, reinforced, all those different classifications that we will see tomorrow in the afternoon for those who want to attend something more general in machine learning. They can be used in all those cases, not just for supervised. Typically, the examples are shown in the supervised case with classification because they are simple, they are nice, and we have data sets cleanly prepared for that. So that's, but this is not, this is not the only thing, the only context in which we use those. After that, we have what we see like a whole zoo of neural networks. So we saw like this one, the deep feed forward. This is what we saw in the figures before, but there are many others where, well, you see the different colors, meaning different ways of attaching those, collecting those, stretching. This one, for example, is something that people use to transform this one, the inverse graphics, to get one image converted into a different image. So taking a photo of someone and putting in the body of somebody else, that kind of things that are appealing. Well, not too much scientific thing happening there, but yes.
And does each configuration have a specific application? Or
pretty much yes. Each configuration of that, they have been designed for a very good purpose. So in particular, those with let's say those that they have like pink convolution or pool, convolution plus pool. Those are using computer vision, for example, for images. They're very good for that. Those that they have those like blue, the blue, they're used, for example, for recognizing voice patterns or signals. Let's say you have a signal from the sky that you want to recognize, you get those because those go with time, and the time becomes recurrent. So they use in those contexts. I will try to see if we can get one example for you at the very end with those recurrent. But for most part, we will be making examples with the convolution. Yeah.
Explain what is the difference between radial basis function neural networks and fixed forward.
Which one?
First and second, because for me, it's no, is it like in the explanation? Yeah. First and second forward, feed-forward neural networks and radial basis functions. Aren't they the same? I mean, linear and like nonlinear functions, and that's it.
Yes, but the fact is that this feed-forward, you see that they have a beginning and end. So that let's say you have something here, and they move into it. So there is a directionality to those things. So they look like the eye, for example. The neuron that we have in the eye is just an input layer. So there is a clear input layer. They move into the next one. They move to the next one. They move until the brain connects. Yes, but these others, the radial, they don't have a beginning or end. It's just a more graph problem. So we have like a connection from one neuron to the other, but that is not a beginning. It's just a nebula, like in our brains. There is no what is the neuron that fires first. No, it's everything there a little bit more connected. That is the idea that is been trying to pass here with the radial. When we have this, yeah. So there is less directionality. That's the point. That's the difference. You get that?
Yeah, but like for example, what input data?
Oh well, in that case, that thing of input data, they just have a state and they are processing. This thing of input fits nicely with this thing. We have an input in those. It's just you have some numbers and they are moving like in a dynamical system. So they have a state, and the state will produce the next state, and with the present and the past, you can go into the future. So that you can see that you can put the points there, and they will start moving. Have its own dynamics. You typically what we see is those would have an input, clear input, and clear output. Okay, so now let's go. Someone mentioned about activation functions and all that. So, so you see the crucial ingredient here are the activation functions. Everything else is really linear algebra, vector multiplications, matrix vector multiplications, things like that. So things that take one number, multiplies by another numbers. We will see for those who are especially undergrad, not familiar with linear algebra, maybe, I don't know. We will have a little bit the opportunity to see how that works. What is a matrix multiplication tomorrow, I think. But just keep that in mind. Again, I designed this workshop to be recurrent, to be like a network by itself. So you have a function that is crucial, it's the important ingredient to make this. And those are the functions that introduce the nonlinearity thing happening in those networks. And there are many. The good thing is that for most part, you just use two. The rectified linear function and one version of those, the logistic or tangent H or R time. So between the logistic between the logistic and rectified linear unit, those are the most popular activation functions that are used in deep learning. The others are functions that introduce some nuances that facilitate the training, that produce better results or faster results, that are better suited for some purpose. There are some that are like a combination of two words, the two main themes here. So like this ELU that looks like a curvy version of the ReLU. Is nice, is soft. the first derivative is sub. You can derive that as many times as you need, and it's sub. So that is something like this. The ReLU, for example, is continuous, but the derivative is not. So that is like a little bit the problem with that. And there are also the facility of compute those things and getting the derivative. So both the equation and the derivative, how the slope of that curve changes in the axis, in the x-axis, that's the derivative. So the first one here, for example, we have a line. With a line, we cannot do anything. If you remove the activation function and you keep a line or put nothing, all that you can do is just rotating, stretching. You will not be able to make a very complex mapping as we require for that. And the derivative of a line is just one number, the slope of that line. For those that are the sigmoid, you see in the infinite limit is 0, in the other infinite is 0, and in the middle it makes the curve. So that is well, actually the derivative like that. And for the ReLU, we have a function that is split in two terms. So it's 0 for all the negative values, and it will return one single number. The derivative will return a single number beyond some point. So again, two typical functions. Keep in mind, we will reiterate that when we enter in the mathematical building blocks of this. The sigmoid function, typically used in classification. The ReLUs are typically used, well, in dense linear algebra, in dense neural networks, the sigmoids. The ReLUs are very popular in those convolutional, so those used in computer vision. We will see about convolutions of that in a minute. And so now I have one example of how this works in practice. How good with time? Okay. Okay. So it's a little bit hard to see, I think, for you. We have three networks here. We have one network here with a hidden layer. And here what we have are symbols, just a symbol. But here you can see on the screen that each one of those neurons, they have some states, some weights. So those are the W1, W2, W3 values for this network. So we have 3 here with the corresponding weights. We have 2 here with the corresponding weights. So just numbers, just numbers. And the idea is to propagate that. You have one input, we have some input numbers. What we are doing is computing the dot product of those two vectors. It means taking the input, the first input we multiply by 1, the second input we multiply by this, the third input we multiply by this. We collect all that, we make the sum, and we put in front of that, with the result of that, we put the nonlinear function, the sigmoid in this case. Sigmoid here, sigmoid here, sigmoid here. If you do the math for those values here, you get 3 numbers. Those 3 numbers, with the weights that we have for this output layer, we multiply. So this number, we will multiply by this one by this one, and the third one by the third one. We sum, we get a number, and we see on the table for the sigmoid, for that number, what is the corresponding output of the function. So what is the output of the function when you get that? The number could be anything, but the output of a sigmoid will be between 0 to 1. So that is what is happening here. we can see this, and if you want, you can execute this, no problem. But you have to execute the first blocks here. If you would like to execute the notebook entirely, you need to start firing this from the beginning, at least from here. Let's say how this works. If you want to make a box here, you can put an extra box, or you can put, let's say, a new cell here. What I do typically is, because I know the commands, is B to add a new cell, below A to add a new cell before, and you can put 4 plus 4, for example, and you hit Shift Enter to execute the Jupyter. For those who are not familiar with Jupyter notebooks, you get that. If you start executing this, so you load this NumPy, PyPlot, all that, you can start making the operations that are happening here. All these operations that I mentioned here for these neurons, you can put them in a nice mathematical structure. There is a matrix. So you can convert all the weights in the 3 neurons that we have here as with the 3 inputs. So we have here the weights converted into a matrix. Here we have the input converted into a vector. And all that we need to do is the dot product. This is a NumPy. This afternoon, for those who are not familiar with NumPy, this is how you make the dot product of a matrix and a vector. And you get 3 values. Those 3 values will be the output of the neuron before the sigmoid, before the nonlinear function. And I think just after that, I put the function there. You get the output. You compute again another dot product from that. And you get the final output of that. So it will be something like this. So you have the sigmoids applying to the result of something that is a dot product of something that comes from the sigmoid. So like a chain of operation. The output of one function became the input of the next one. So there is an instruction. But at the end, you can put this entire network in one function, in one line. Is sigmoid or the dot product of the sigmoid or the dot product of the input, something like that. That is what the neural network is doing mathematically. Just matrix multiplications. For those of you who will read again, we will reiterate this. And there is something else that those things have inside. I mentioned the values, the weights, the 3 numbers that they have. They need 1 number for each input that is receiving. So the 3 numbers plus a 4th number that is a bias. The bias is just shifting the location where the sigmoid will be applied. It's just moving things up, so make them fire better, so getting closer to 1, or shifting down, so they will be less, returning a lower value, no matter what happens with the input. So they are moving in this direction. They are playing in the 2 ways. Yes, tomorrow we will see how that translates the linear algebra into an affine transformation. But that's it. So we have biases, then nonlinearity. And now we got an answer. We got an answer here. At the end, we got 2 numbers here. Now it comes the tricky part here, is that we want the network to produce an answer that we want. We decide what should be the answer, the design. So now the whole thing is to figure it out how we need to change all those numbers, all the weights, all the biases for all the neurons to get what we want. And that is what is called the backpropagation. And the backpropagation has two ingredients, basically. One, we need to know what we want. We need to know a function that tells us how far we are from what we want, and a good way of changing the parameters, all the weights in the right way. So the next time that we run this, we get closer to the right answer. That is the thing. And we have a good luck. We prepare that in a way that is mathematically easy to do. Because for those functions, both for the linear mapping and for the nonlinearity that we're introducing, we can take advantage of something that not always happens when you are doing this kind of problems, optimization problems, is having something where we can take a derivative. The derivative can help us. It's not, there are problems where the derivatives are not feasible. All that you can do is to try to encircle the solution, or trying to throw random dices and there are methods for that where derivatives are not feasible, or the problems or with the derivatives are not so well behaved. There are other solutions, but here we are lucky. We have derivatives. We have ways to know how the slope of this is changing, and we can move in the direction to minimize a certain function. The function that we were minimizing is what is called the loss function, is a measure of how far we are from what we want. And the derivatives will help us to go into the right direction. For the backpropagation, you see here those networks, and you can think of them. And there is a dependency for this neuron from all the others. So we can compute what is the change that I will be incurring if I change this one a little bit, or this one a little bit, or this one a little bit. But at the same time, changing this is a function of the input. So we need to go into how important is changing this one, how important is changing this one or this one. All those will cascade in a set of dependencies on how the derivatives, or in this case, when we are talking about a high dimension, how the gradient changes with respect of all the other variables that we can depend on, let's say, recursively. That is where it comes the mathematical, more trickier part of this. It has been solved very, very efficiently, but a technique that I will show tomorrow in more detail. But let's keep it like this, at least for now. So we have a function, and from that function, we can take derivatives. So we can take the gradient. Yes?
How do you do this if the network is not converging?
What do you mean?
Like, for example, if the neural network is not converging, it's like we're going to do like chain or Boltzmann.
Well, that could happen, but typically, well, it depends. Yeah, sometimes it will. You will have something, or not converging, or converging to something like a stacking in a solution that is a minimum, but it's not the global minimum. So it could be a stacking on something. It could be just jumping back. But what typically happens is if you put what is called the learning rate sufficiently small, it will be moving slowly and will sit probably on a situation where the derivative is zero. So it means, okay, it should not change because now everything looks that if I move everywhere, I will be climbing. So I will stay here. But maybe down there is a better solution. So for that, there are ways to jumping, to escaping from locals. There are a few things. But typically, these things are so high dimensional. The word in high dimension is very different from the word in 3 dimensions. To give an idea, if you put random distribution of points in 2 dimensions, and you count the average distance between 2 points, you get a nice distribution. Yeah. Now you think about that in 10 dimensions. You get like a delta, a huge peak. So when you move in more dimensions, the distance, the concept of distance is very different. The distance are huge. You think about it, you think, say, on a plane, take point, take distance. Now take a cube, compute the distance. Now imagine in 4 dimensions and you compute the distance, Euclidean distance. The square root and the sum, the square plus the square plus the square, all that. 10 dimensions, this distance becomes bigger and bigger and bigger as you increase the dimensionality. Also, that includes all the paths that it can follow. So it will get more flexibility for that to change. So that thing that is typically happening like in a small dynamical systems where you have chaos with all of this, that stuff. It could happen here, basically running a dynamical system, but it happens differently and less often. That's it. Okay. Okay. So I will be going here to jump into the final part of this notebook, which are a review of the milestones of neural networks. Oh, by the way, well, let's say the backpropagation has been solved. There are several techniques to make it better, like knowing that you are moving in a location that is mostly flat. Well, you should feel comfortable to run faster. If you are blind or a short sight, if you are in a flat surface or something that you feel more comfortable walking around. But if you are working in something that is bumpy or rock, you feel compelled to be more careful, look more. So that is something that is put in practice when you try to train those networks. And one of those techniques is the idea of momentum, to follow where the network is going forward and trying to guess better results in advance. Well, okay. Neural networks has been around for a long, long time and have changed names over many, many years. So before artificial intelligence was basically born in a conference in '56. At that time, or well, after that, people believed that the way of solving problems was to offer the computer all set of inference with statements, and the computer will take those inference into account and produce results. That is the old-fashioned artificial intelligence. After that, one of the pinnacles of that was in the 80s, mostly on 90s, beginning of the 90s, with expert systems who could identify illnesses with a very narrow area of domain or domain of expertise, hard to manage, hard to maintain. So that was now deep learning. Deep learning has changed names. It was called before in the 70s cybernetics, in the 80s connectionism, and neural networks in the 90s, and that name still sticks with us. And the current name is deep learning. And by the way, be careful with that, with those words. They become very quickly buzzwords. Machine learning, deep learning, big data, all that thing looks fancy. So you need to scrap all that garbage from what it actually is. The machine is not learning as we understand learning. Have no better understanding what it is doing. not real understanding. In artificial intelligence, what you think as intellectual activities doesn't translate into consciousness. So we are not creating machines with a conscience, at least not now. So that is something that you need to put aside as you move into this. The first deep learning networks started emerging back in the 2000s, and some maybe appeared in MATLAB or Torch at that time. Torch was a project in Switzerland, I think. So at that moment, it was something very, very narrow for a subset of very tiny groups of specialists in computer science, in artificial intelligence. The big bump of this happens almost 20 years ago with AlexNet. Alex Krish has, I'm not able to pronounce that. Sorry. From Toronto, they published a paper where they were able to beat an image recognition that really jumps before after the second place in that context. So that significant change in image recognition brings the attention a little bit with some inertia, as is typical from science. The fact that those things could produce some. So that is a network. We will see how AlexNet looks in a minute. But that was the beginning of the big hype of deep learning. After that, in 2015, 16, another network that we will use if we have time today, or otherwise tomorrow, ResNet, that was also a big jump into image recognition problems. And at that moment, we have Caffe, Chain Artiano that no longer exists or no longer supported, or became inserted into some other frameworks. One of the reasons why this got big success was big tech companies. Each one of them started building development groups. So Google has its own, its TensorFlow, and after they put it available, Facebook later took PyTorch, Amazon, CNTK, it is no longer actively offered. Amazon, with Amazon Web Service, they support mostly MXNet. So big tech companies, because they rely on mining everyone's data. So we are not the clients, we are the cattle for them. And they became very effective on mining that data. And so they put a lot of money on that. Image recognition is happening every single day on a cell phone. When you ask for something, when you get a recommendation for a movie, when you get even the loans, everything is happening behind machine learning techniques, especially deep learning techniques that recognize images, recognize your preference, recognize your life, what you will be doing, your political orientation, sexual orientation, your financial capabilities, everything. They mine everything, and with that, they sell that information to who can pay for it. And so that is where this got a lot of money into that, around, well, from 2012 to, up to now, basically. ResNet in 2016, another big success. We moved the bar significantly up. And here is the link for the paper if you want to see. At the end of the workshop, what I expect is that you can take this paper and you understand what the paper is offering. And now what we see, and at that moment, there was like a Cambrian explosion of different alternatives, of different frameworks. And what we see now is like a consolidation of those. And we end up with three, basically three: TensorFlow, PyTorch, MXNet. I don't know if they will survive in the next 5 years, who knows? But my spirit is that you should be learning a little bit of each, so you can abstract what is important, what they are doing, and not feel attached to one. It's always important if you plan to move into a career in this, not just to have just one option in your curriculum, but have at least several. So that is another thing. And now what they have, and now the other thing is that thanks to gamers, we have to be very grateful to gamers, because they basically roll back the explosion of GPUs. These machines, these devices, people pay like an important amount of money for big boxes that are capable of running games at 120 frames per second, and they are super happy with all the anti-aliasing, all the stuff. They put that in Max, they put the big screens, and that looks great, and they pay big bucks for that. And people, companies like NVIDIA, use all that money to create those devices or GPUs. For scientists, they are very expensive, but for them it's a niche market. The big market are gamers. Those machines that we use are very expensive, that we have on Thorny. We have, for those of you who will not know, we have RTX 6000, we have A100s. For those of you who knows what I'm talking about, so they are very expensive machines. One of those could cost $7,000. So it's not something that a gamer with a normal father will buy. So now people is training those massively. So training with mini GPUs on many computers, distributed platforms. So that is what I'm talking here, large scale training for modeling the climate, for modeling the market, stock market, many, many things. So all that through the trends. Here, I will show you just the books that I own, that I have, that I use, that I took. If you see here, you will later on that I took ideas, portions of data from many of those books. So I have like a selection of machine learning books first, very general. From the simplest, I put them in my order from the simplest, from the most approachable to the most mathematical one. And here the same, this is a very book for those who just want the narrative, or want to know how to explain this to your father, your grandmother, whatever. Deep Learning is a very approachable book. And I collect things, ideas from many of those books. Here, more practical books specific for one of those frameworks. This one is for Java, so they have a nice introduction, but there is a little bit outdated. This is a more mathematical book. So this is just a book where they have all the equations and then in all its glory. That means that the book survives the pass of time because it's the math. While these other books, I have to buy the first edition and after the second edition, and because all those things change. And I recommend especially this interactive book very much. You see this Dive into Deep Learning. If you want to see like a homework, to give a read to the first chapter of this book. It's very narrative. It's like what I did today to this point, but with more elements, with more links, with more concept. This is really good. And they offer examples in the 3 frameworks. That's another good thing. They are mostly specialized in TensorFlow and PyTorch. No, in PyTorch and MXNet. And now more recently, they introduced material in TensorFlow. Very good book. It will be like a book of 1,000 pages if you put that into a real paper. Some slides, I recommend this one, John Urbanix. This is like HPC is a little bit like what I do. I am computer science, computer physicist. I'm a physicist by and software developer. He is a specialist in parallel computing, and he offers a workshop. If you go to PSC, they offer workshops, and they will be offering one in August 30, I think. So you will see a lot of this material is just deep learning in one afternoon, fast pace, much faster than I'm doing here. They show very nice stuff in this. In this is one slide of that. If you want to attend, it's free. It's the Pittsburgh Supercomputer Center. It's very good. And this is a blog where I took the images where you see all those animations. They are very nice. And they have a very nice, approachable description of backpropagation, which is the hard topic of deep learning, is the backpropagation, how you get all those connections, derivatives, moving on. And a set of Jupyter notebooks, they are becoming a little bit old by now, but I used them at some point. And those videos, this one is really good. They have like 3-4 videos. This last video on the YouTube channel.
He's like my favorite mathematician.
And yeah, very good. And this one, Yasser Abud Mustafa, is also a good material for deep learning, for machine learning. So there are some things we will see. I will be taking like, okay, 5 minutes, and we will be starting the next notebook. So if you go, if you want to open it, and I think I will be moving on. What is this? Oh, so 5 minutes, we continue. We will start with our first neural network, the handwritten recognition problem. We will start creating multiple networks, exploring, okay, what happens if we go bigger? What happens if we go deeper? What happens if we change the mind and we use something called convolutions? So we will be exploring all that in 5 minutes. So relax, I think around we have restrooms if we want.
Swap your laptop over here. That way the webcam would be hitting the, I don't know if you're not gonna use the whiteboard, then it doesn't matter, but.
Sorry, what's it?
Swap your laptop over, move all this stuff out of the way, and move your laptop here so that the webcam is hitting the whiteboard.
Because when I move this, I'm not.
Because I can't get the, I mean, this, I don't know, it doesn't really help that much. But if we move your laptop, because your laptop has a webcam too.
Yes, but the point is that I'm not using my laptop for the presentation. I'm using this.
Yeah, but you're in Zoom, so they can see it. I don't know.
Because I am not on both accounts. I am connecting both. I am connected here.
That's why I just noticed that you have those. So.
Okay. So let's follow your suggestion. Bad idea. Something like this. It's the keyboard.
Now.
Well, no.
ask you how we got to these files? How to get to this like Jupyter directory?
Got into the.
I've gotten to on demand and onto
Yes.
like the interface. I haven't got to find the Jupyter notebook.
Okay.
Yeah.
I got a question.
Yes.
Actually, professor's correct, right?
Well, I'm not professor. I'm not technically professor.
So this is all the
I don't
users.
teach for grade.
I thought that maybe it'd be here, but
What did you?
so
Yes, but you don't go there that way. You go here. And you are connected to Jupyter. And it's from here where you can go. Where you scratch. You have not copied the data. Probably because you arrived late. And so
is it in GitHub somewhere?
No, it's there on the computer. But allow me to copy that for you.
Sure.
So rsync.
Oh, okay, that was
minus
the command.
the command that we put on the screen at the
Okay,
moment
I saw that. And I was,
share.
I thought that you're maybe doing like this in R or something. So it's like maybe wasn't for me.
The share tutorials, deep learning, remove the slash to your scratch.
What is rsync?
Rsync is a command for copying files with the advantage of idempotency. So it means that you applied or something that already was applied will not do anything.
Okay. I'm only seeing.
So
like,
you copy what they have changed. That is the point.
and
So
is that a native? Because I've seen like curl.
it's
and
on
stuff like
any Mac, Linux machine, you have rsync.
Okay.
It's a very common command. It's better than CP or the typical command that you learn when you're just starting is CP for
Okay.
copying recursively.
Sure.
But this is more for copying.
Okay.
So it completes. So notice you copy the data and you try to execute the command again, nothing happens.
Okay.
Because the data is already there. So now,
Cool.
so now you can go here into Scratch. Now you have a folder deep learning. You have the notebook. You can click here, and you see the notebook, and you can go and execute all this. So you see the material. You can go and execute the notebook. So
Excellent.
one way of executing the entire notebook is restart and run all. It will run all the code from the beginning to the end.
Cool.
It will take like a few seconds.
Thank you so much.
Okay. Somebody else have a question or something?
I have two questions.
Yeah.
Are you going to cover how to work with the HPC or no? Is it just basics of the deep learning?
Let's see what you mean by HPC. What I understand when you say learning how to work with the HPC means command line operations, entering, executing jobs, submitting jobs, all that. Yeah, more. In principle, no,
Okay.
because it will be a little bit outside of the introductory term that I'm attached. So I'm attached to be simple, even for people who are not familiar with Python.
If you go onto YouTube and just search WVU research computing,
Okay.
we have a YouTube channel on there, and we've had introductory workshops we've done before. If you want to watch those,
Okay.
that would probably be good.
Okay. Because I have my codes. I just want to run them in something that is fast because my office computer, laptop, these are not working and I need to use GPU stuff like that.
So this is more for.
We have specific workshops for GPUs as well. We've done.
I
For running
think
on
so.
GPUs.
Yeah, well, yeah,
So
right.
if you look those up, we have those. And you just watch those. Because we're using the same system in those workshops that we're doing now.
The reason is this is not how you actually use the cluster for big runs. So we are really training big stuff. because it will take a long time. So that for them, you submit jobs. I maybe can show something like that at the end. How you train a network without the Jupyter notebook stuff. So just a Python script that you will be running, how you write your submission script, how you submit, how you request like 1 week of execution. So you can have something big that will take 3 GPUs for 1 week, and you can train with them. So there are ways to, at that moment, you will not see in front of a browser for doing that. But maybe I can show you something like that, simple. But no, for someone who already knows command line and editing files, so Linux, Unix, is familiar with that. Otherwise, I will be converting this into an introductory to HPC. And so that is the balance there. And
the other question was that, does WVU have any cloud access instead of HPC?
No, what we have is, well, he runs a cloud thing.
Yeah, that's for business D&E students specifically.
Yes.
For a specific master's program.
Yeah, but most of the users that we serve, they run on our cluster, so on-prem machines, machines that we have.
Okay.
There are solutions, and you are free to use them. You run for research, you get money for that, to running on AWS, so you can get instances there with, I think, SP3 or G. There is SP3, is that has GPUs? I don't remember then the names of that. So there are instances that give you GPU on them, storage on them. So you can train those. Azure offers something that is very specific for each cloud vendor, let's say. And we are concentrating more on the neural networks with the frameworks, using the cluster on our web interface. So I am limited by making this very introductory.
Yeah, I understand. I just want to make out of my time, and basically I have worked with all of this. So maybe this is not.
And again, for this afternoon, for all of you, this afternoon will be Python, or just Python, from variables to classes to the standard library to NumPy. If you are familiar with NumPy, if you are familiar with how you manipulate the slice, indexing, all that on a NumPy, you can skip that for tomorrow, and we will not be discussing deep learning this afternoon. It will be just playing in the field so everybody can learn and don't sit in front of a code that is completely unintelligible for them. Okay, so now we will go into exploring. So please go and open the second notebook. So it's chapter 1B. I will be executing this step by step. Again, I'm not using the GPU for this. Yes. So this one is just something that. Let me see. I will clean all that. Okay. And so forget about this. I'm loading this. This is just WordPress, nothing. I will be using for this notebook one of the most popular deep learning frameworks used in the industry, for teaching, for anything, TensorFlow. There are two versions. Version 1X is kind of, nobody uses much of that. It's still, except for those who got legacy codes that they don't want to change a lot of that. But what we will show you is the latest, with the latest version of TensorFlow. So I will be executing this, and you can go and execute this with me step by step. We will go with each thing. So here it's telling me that I'm not using the GPUs or using. Okay, so I will be using NumPy, which is the standard de facto for manipulating matrices. This afternoon, I will show you how you should be using NumPy for all scientific purposes. Second, if you have loops in with arrays, you are probably doing something wrong, or you don't know how to program in NumPy, and you are probably a C programmer trying to translate your code into Python, which is wrong. So many of the operations, there are loops or happens directly without explicit use of a for loop or a while loop or something like that. And the other thing that we will be using is TensorFlow. The latest version of that code is the 2.91. And again, this is one of the most popular codes. What I did here is that I have this code flexible enough so you can use CPU only or GPUs. I know that if I use GPUs, I will be like 60 or 50 times faster. Still, this is simple, but I just want a more fluid conversation. So what I'm doing is, if I am running with CPUs only, I am just reducing the number of iterations that these neural networks are doing all the time. I'm just cutting the number of cycles to the half. We will still be able to get the ideas that I want to transfer to you, what those networks are doing. So I just cut it. If you are running this on a machine, if you are a gamer and you have at home a machine with a decent GPU, but a decent GPU is something like an RTX, something that is like 5 years old, is probably fine. And a Mac, except someone told me that they could be able to use the GPUs on the latest version of Mac. This is a Mac from 2017, so they don't have that. They use a different brand for cards, so they will be on CPU only on this machine. But you don't need it. This is just something simple, just to learn to feel what you have to do. And this is a very classical problem. You will see this on every single book of deep learning. The classical NIST data set, handwritten digits. The story behind this is the NIST creating 2 data sets. One was from employees of the NIST, the national standard or something. And another set was from high school students. They were asked to draw numbers, and they took photos of those numbers and put those photos, center the photo, put that nicely on tiny rectangle squares. So let me see here. So they originate with 2 data sets. And of course, what you expect is that, well, employees were a little bit more careful, and you cannot expect the same from high school students. So the quality of the 2 data sets became slightly different. The story is there. The point is that they put the digit into a grid. So an image that had 28 pixels on this direction, 28 pixels on this direction. And this is, so they have a total of 60,000 images of digits. And the another good thing is that this is a very well balanced data set. This is something that you typically don't get in real life. Is that the same number of, there are the same number of ones, twos, threes, four, and so on. They are perfectly balanced, which means that accuracy will be a good metric for us. It will be something that we can use. Real life is not so bad. So we have two sets. We are separating. This is very typical from machine learning. We separate two things. One is the training data set, the training set. Another will be the test set. The test set is something that you hide, you put aside. You never used to train the network with that. It's something that probably is with your boss or something, so you don't feel the temptation to use this. Also because data is very, very valuable. So you can feel tempted to use that I want to use this one. No, you should separate that, because something that happens often in machine learning, or especially in deep learning, is that the learning becomes remembering. And we want to avoid that. We want abstraction. Being, again, learning is not learning for us, for humans. This is what we think machines will be doing if they will be trying to learn. This is, we don't want to remember. So remember is like when you have a professor and tell you, okay, the exam will be one of this exact exercise that we have, and the exam will be one of those. So that is telling you that you are not capable of learning, you're just too remembering, and you just take that, copy, okay, what I have to solve for this problem, for this problem, for this problem. One of those problems will be in the exam, so I just remember. Learning means that you are presented with something that has not been before in an exercise, in a whatever, and you are capable of solving because you got the abstraction. Some professors could be conscious that you are not learning when you are offered just to remember. So that's the importance of separating a training data set, a test data set. Sometimes you even separate a little bit more, and you separate some data to tune your model, to make improvements. So that will become what is called a validation data set. So let's do this. Another important thing here, if you want to run this on your own computer, feel free to do that. At that moment, you don't need to do what I'm doing here in this one, loading the data from a folder. So I put all the data in this folder data, in one folder up in the deep learning folder. There is a folder data, and there I store the data set there. The reason for this is because on the cluster, you don't have internet access when you are running on a compute node. So you need to bring the data first and run. So that is one of the things that makes slightly different when you are working on a cluster like this. Otherwise, you can do something like this. So I put the trick here. If you want to do this on your own computer, you can just load TensorFlow, Keras dataset, and MNIST. They bring the data for you. And they also, with the command MNIST load data, they will return the four arrays that you will be using. So we have 4 arrays. The first array are the images, things like this. We will see how they look like. Another is a big vector where it says, okay, the first one is a 9, the second is a 7, the third is a organic. All labeled for each image that we have in the training. Also, another good thing is that they scramble the whole thing. So, and you need to pay attention to that. Otherwise, if you say, okay, the first half is my training set, or the 70% is my training set, and my 30% is my test set. If you are not careful, you got all the numbers from 1 to 7 in in your training set, and the 8s and 9s in your test set. So you need to scramble that thing. That thing is doing all that, the scrambling. So you see there, if you are familiar with NumPy arrays, I forgot to execute this. So now you see on NumPy arrays, this is something that we will see this afternoon. One important concept is the shape. So they store ways, the data in a multi-dimensional array. And the way of knowing how many elements we have on each dimension is called the shape. So here we have 60,000 elements in one direction in the first rank, in the first axis. In NumPy. 28 in another direction, 28 in the other direction. So it means 60,000 images, 28 times 28. The labels is just 10,000 images, 28 times 28. And the labels, I told you, is just a vector saying 7, 8, 9, this. So it just have a categorical value, just one number associated to it. Same thing, 10,000 numbers for this one. I will be showing you a little bit how this data set looks like. Is something like this. So on each point, they have a number, it's an integer, using 8 bits. So you go from 0 to 255. And those represent the numbers. And here you will see the size of the image. And here I am showing you one of them, how they look. So you get an understanding of it. So you see here zeros everywhere, mostly. Big numbers around here. You see, I put the actual number on top of each reticulum, each grid. This is the number. This is how this was built. A big 60,000 things like this. And for the corresponding index where this image is located, you will see a file. And the first thing that we'll be doing is that typically neural networks are happy working with small numbers. So something that goes from 0 to 1, something that is usually floating point numbers. So the first thing that I will be doing is taking all those numbers, changing the type in a NumPy. NumPy is an array of numbers, numbers of a very specific type. So this is not a data frame. You don't have a column with numbers and another column with names and another column with dates. This is a data frame. This is a NumPy array. All the elements in the array have the same type. And you need to explicitly change the type. So I'm changing the type to a floating point number with 32 bits. And after that, I'm taking that number that is go from 0 to 255, and I divide it by 255. So I am getting a number from 0 to 1. This is what I'm doing here. And here I will be starting with our first neural network in practice, how this works. We will be using Keras. Yes. Just to get the number that you see here, the pixels go from 0 to 55 to 255. So 0 is black, 255 is white. Now, if you divide that by 255, you will be getting a number that is 0 here and is 1 here. So we will get in a number that is not exploding in the scale. It's something that is constrained to 0 to 1. So the network will work better with numbers that are normalized somehow. So this is just, there's something that facilitates the manipulation of them. And also the fact that we convert this into floating point numbers, because otherwise you will be having like jumps. If this is an integer, imagine a neural network that is just filling this with integers, it will be jumping from 6 to 7, and after that, it will not be a smooth curve, so it will not have a good derivative, so it will be a nightmare. Okay, another thing that we will be doing is, where are this? Okay. Oh, another thing that I did, I forgot one thing, is I was reshaping the array. In NumPy, in all those multidimensional arrays, you manipulate those arrays all the time, and no data is moving in the memory. All those things happen without actual movements of memory. That's the magic of NumPy. We will see this afternoon for those. And one of the things that I'm doing is I'm saying, I don't want this as 60,000 arrays of 28 times 28. I want just 60,000 arrays of 784, I think, 744 numbers. So I am flattening the array. I am changing the dimensionality of this from having, let's say, in mathematics, we say tensor. This is changing from a rank 3 tensor to a rank 2 tensor. So I'm just changing this for a big matrix. A big matrix that has like 60,000 rows, 784 columns of numbers. And after I am converting that into floating point numbers, real numbers truncated, and divided by 255 to get some number from 0 to 1. So now, this is the simplest way of building a neural network. Is using Keras, and Keras is like a high-level library for making these manipulations very simple. Otherwise, you have to go deep into the how TensorFlow works for creating those tensors by hand and all the machinery. This makes things simple. So this is a sequential network. Remember that the networks that I show you, they follow this pattern. They have an input layer, they have a hidden layer, and they have an output, right? Here, we took the vector of the numbers and we flattened that vector. So we have 784 inputs here, numbers. We will be moving this into a 10,000 elements here. So really large thing here. And finally here we have just 10. So 10 here. What is it? Oh no, oh, 64, sorry. 64 here, 64 here, hidden layer, 64 here, 64 here, and at the end, 10. And all they are connected. So this one here is receiving inputs from all of them. Every one of those is receiving inputs from all the 64 here. And every one of those is receiving inputs from the 784 here. This is a dense connect, 2 hidden layers, 700 here in the input, 10 in the output. Why 10 in the output? Because what we have is a number from 0 to 10. So we will be separating it. Why we have this 784 here? Because that's exactly what the image, when you stretch that image and we take the pixels one after another. And we will see, we will be using this activation function, the relu. So here, what is happening is Wi times xi. Here I am using the Einstein convention. So this is a sum. This is something the physicists use. We understand this as a sum. We are summing this. We want to see more explicitly equal to this. So how many we have here? We have this number. So one of those. Let's concentrate in this one, for example, that I did very explicit. Inside this, imagine that inside this I put 784 weights numbers. 784, one for each input that this thing is receiving. What I'm doing is taking the weights from here, multiplying by every one of the inputs, and adding the bias, and putting this into a function. And the function that we'll be using is a function that will return 0. If the output of this thing is negative, it will do nothing. It will return the same number if the output of this thing, the output of all this sum plus the bias is positive. That is what this network is doing. And that is what it's doing on this layer. That is what it's doing on this layer. And on this layer, I'm doing something slightly different. I am using a softmax. I think that I describe it here for the softmax is. This is the idea. You get at the end of this 10 numbers. And with those 10 numbers, we need to decide if this is a 7, this is an 8, this is a whatever. So what we want is that this offers us an idea of probability. One good function for doing this is something that, first, these numbers could be negative, could be very big, really negative, and we need that to squish in something that is positive. Yeah.
They can't see the blackboard.
They cannot see the blackboard?
Yeah, they should not track.
Why? Do you move?
Yeah, can you rotate your laptop a little bit first?
Oh, okay. Like this. What about this? It looks better? I don't know. Okay. So, so what I'm doing here is this points again. So we have here the inputs. Yeah, we see the input here, the hidden layer, 10 numbers, and we want those numbers to represent probabilities. One good function that smashes big numbers, reduces things that are negative into something is the exponential of the number. So, we'll see that in so the exponential of the number. I was using this here, and after I will get in numbers here that are positive, and I would like them to become like probabilities. One way of doing that is dividing that by the sum of all of those. At the end, I will be having 10 numbers here that when you sum them, by the way of our construction, it will return 1. This function that is doing this is called softmax. Is making a sum, is smashing numbers that are negative, big, returning something that is just positive, and after you are smashing the numbers, so you get something that when you sum them, you get 1. And you will use that to hold the system in a minute to improve, to get how good or bad this is in identifying this as a number. And with that, we will be training them. We will see that. So this is how the
There's someone else who had a question.
yes, how we know which output not belongs to what number. Oh, yes. So it's our decision. So we say it's our decision. Here I will be storing this the 3 dots here, here, and we say, okay, whatever is in this output is my representation, is my probability of this being a 0. Whatever is in this will be my probability of whatever was in the input to be 1, to be 2 here, and to be 9 here. Of course, at the very beginning, you put whatever you want in the weights, whatever you want in the bias, so it will be completely off. It will be really bad. It will be basically saying, okay, probability is 0.2 here, 0.1 here, 0.3 here, 0.0. It will be whatever. It will be garbage. What the whole point is to use and reuse this network. So over time, if it's presented with pixels that we know they are 1, this value here for the 1 will be going higher and higher and higher. Ideally, will be significantly higher to everything else. And if it's something else, if the value that will be flashing, it will be the value corresponding to the digit that we want. That's the whole thing. And not necessarily. You can decide that you can decide this. Perfect. I can put this. Oh, this is for 1. This is for 3. This is for 5. And I put all the odd numbers here. And after saying, okay, this is for 2. This is for 4. This is for 6. This is for 9. The ordering of this doesn't matter. What matters is in a minute when we use the loss function, how we define the loss function to be consistent in such a way that once fire this one, 3s fire this one, it will be associated in the loss function. So your way of representing the ordering has not meaning at all. It's just this plus the way you define that. Why we have 64 in the input? No, not 64 in the input layer. We have, this is the input layer, is 784. This is called the first hidden layer. So this is the first hidden layer, it's 64. Why 64? That's an interesting thing. And it has to do mostly, you can put whatever you want. You can put 30, you can put 17, you can put a prime number, that's hard. In principle, you can put whatever you want. Of course, you don't want to make it too big because too big it will be hard to manage. By the way, there is one theorem in this thing, is what you can fit whatever function you want with just one hidden layer. You don't need more than one hidden layer. In theory, the problem is that this hidden layer could have billions of numbers to fit correctly. So it's impractical, but you only need one hidden layer. So this number here, the number of neurons that we put in the hidden layer is completely up to you. What you put 64 is because 64 fits very well. Everything that is a multiple of 32 fits very well in the way, the internal way, for those who are programming CUDA. They know that there is a magic number in the CUDA devices, because the internal threads, they work like in blocks of 32. I will not go into the details of CUDA or GPU programming, but that is the origin of the 64. No, it's just a practical thing with the GPU, where those things typically are used. But no, there is no other reason that constrain you to put 64. Actually, one of the exercises for today at the end is to start trying with something else, with put numbers and start making making fun with this and try with something. I will want you to be economical. I want you, okay, you are from a poor country and you don't have so if you have the network at the end, what will be the minimal thing that will give you 95% of accuracy? So can I do it in those Raspberry things? Well, Raspberry will be better than, will be capable of that. But imagine that you have a very cheap thing. So what is what you can do? Okay, 74 here, 74 here, 10 here. That is exactly what we have here. Our in our definition, a sequence of layers. We have got the input 77. So the first one is, we don't declare the input as a layer. We declare that we get 784 values in the input. So we have 3 layers. Dense layer here, 64. Dense layer here, 64. A dense layer here, 10. Activation function, but the end is a softmax. Oh, wait. Okay. I will. I didn't execute this. Okay. It's telling me that I'm not using the GPU here. I didn't ask for one. Another thing that is really good in this TensorFlow is that they will give you a summary. I will help you to read a little bit the summary. This is important for the exercises. We have 3 layers. And here, look at the third column in your notebook is the number of parameters. Those are the number of weights plus biases that are in that layer of the network. So 50,000 parameters there, 4,000, a little bit more, as 4,000 parameters in the second hidden layer, and 650 in the final layer. So where did it come the 50? We have the biases. So we have 10 biases here, and we are connecting this with 64. We have 10, so 60 times 10, 64 times 10, 640, plus the 10 biases, 650. Why we have this one here is the 784 here times 64, plus the 64 biases. So we have all those numbers. So at the end, they tell you, okay, your network will have 55,000 variables or things, levers that you can move to make this produce the right answer for you. So you will have to find that. How you can do that? Well, if you are dummy, one thing that you can do is start making numbers or randomly. Trying those things will never work. Too many. We will use something that takes advantage of the derivatives to go into the right direction at the right pace. The softmax, I mentioned that. Okay, so let's go here into this one. And this is just to show you what happens with the softmax, with some number that just made up. So if you produce this, you will see numbers here at the end that they sum 1. So that's the purpose of that. Just show you. Yes, question? Yeah.
Just to double check, because you have number of parameters, is that are the number of parameters related to the efficiency of the network?
Yes, partially. It's a good and bad thing. The number of parameters is a good thing because with more parameters, you can change more things. It's a bad thing because with more parameters, you can start remembering rather than learning. So you can put, let's say, imagine that those parameters, imagine that this is a black box, and you put tiny little beans inside with 65 65,000 little beans there in these big black blocks. And you ask the, okay, when you see this number, tell our master that this is a 5. And this guy will take, this has its own parameter. With that parameter, you can remember that this is a 5. The second one, you can remember that this is a 9. When you get the grid, this is a. So you have, imagine in this in this mental figure, then we have 55 possibilities of remember whatever the 55 cases that present you at the very beginning. And when you exhaust all those 55,000, okay, you don't know. But you remember, you don't learn, you don't. And after that, you can just throw whatever. So it will be something that learns the very first 55,000 and that remembers the very first 55,000 and learns nothing. There is no learning in that. It's just remembering. So if you have, instead of that, you have 5 million parameters, or there is a big chance that you can remember things when you have just 60,000 cases. So more parameters increase the chances of remembering. In this terminology is called overfitting. We will see that in a minute. So total number 55. I will show you the softmax. And this is a little bit what happens when you do that with these numbers that I just bring here. Yeah.
So how to decide the bias value properly? Like how do we choose the value itself?
All the values, the weights, and the biases, all those parameters are changed thanks to a technique called backpropagation that will adjust them in the right direction. So the next time you want this, you are presented with a 3. It will be changing this. So the next time that a 3 is presented, the same value is presented, the weights are in such a way that with the inputs that they have here, it will fire higher for the 3. This will depend on all the parameters and the inputs on the previous layer, this one, such that those get the right shape or the right numbers, so they fire 3. And this one should change the weights in such a way that presented with the inputs here, return the right parameters here, that will return the right parameter here, that will go. Look at the cascade of operations. It's a string of operations that is happening here, a cascade of things. What is happening with those is taking advantage of the gradients, the derivatives, which one should go higher, which one should go lower, depending on what I change from this one and the weights from before and the values from before. So this is a long change of operations that we will see tomorrow. How those things. You are not controlling directly those. You are controlling indirectly thanks to our recursive way of presenting new numbers, new images here, returning new outputs there, new images here, and this thing, it will be changing all those. So it satisfies that this is 3, but the next, when you present a 5, you also should find here for the 5. So it's a compromise. It's getting the right 3s, but also getting the right 5. And all that is doing recursively training many times. Yes.
What's the difference between like taking the weights and the biases and squishing them in forward propagation?
Squishing, what do you mean by squishing?
Like the sigmoid or the ReLU.
Oh, yes. The sigmoid will squish them between 7 to 1, which fits better for this kind of problem. Yeah, fits better for some problems like classification. The ReLUs usually go for imaging. It's just the people have experience and gain some intuition, which activation, which ways of introducing nonlinearities work better than the others.
Yeah, I understand that. Is that like forward propagation?
Yes, when you have the network already trained, you use just the values to propagate this forward. So you move this one to the output. The back propagation is to get the wakes better.
Is that happen during training?
And this is happening during the training. This is the training. Actually, this is the training. So you get values like this. You see here first the value on the top. You see that's what we get from a softmax from the values that I offered to you. So you see, oh, it's a 5. The number that I present on the top is a 5. What I'm showing you here is that there is more richness in this if you present this in a log scale. In a log scale. So here you don't see this, and that's why we see in a moment why we use logarithms here. So in this way of doing things, we will be compiling the model. It means taking all these specifications that I just present to you here from this model and arranging all the machinery that is happening inside that. For TensorFlow, this is like a graph, and it's basically realizing what is connected with what in which way. So how things should be presented, which is the optimizer, which is the method that I will be used to change the weights. I will be not going to the add-on at this point. What is my function that allow me to decide how good I am doing here? The sparse categorical cross entropy. It looks really scary with that name. The whole thing is a little bit is like here. Is first you can imagine. Okay, I would like to know how bad I am doing here. Imagine that you get something. You got here something that is like a 3. At the very beginning, this is so bad that you put, okay, 0.4 probability that this is a 5, or 0.1 here, 0.001 here. It will put something that when you sum, it will return 1. Okay, what you can do? One is, okay, what I want? What I want is that this one, that I decide will be the neuron associated with 3 should be 1. Should be 1. And all the others should be 1 for this one. So let me see here, put it in a different way. So let's see. Okay, let's go back to the ordering of this. So 1, 2, 3, no, 0. It's the traditional way. So 9. This is what I got from an ugly first neural network. Is that I got, oh, I need the 3 here. For the 3, I put a 3 here, and it was so bad that it told me that 0.4 here, and 0.1 here, 0.001 here, and everything here else, it will be whatever is needed to get this something 1. And what I want is that this returns 1 in this location, 0 here, 0 here, 0 here, 0 here, 0 for everything except that. Okay. Okay. How I can make a function that tell me how bad I am on that on my train? Oh, well, we can think, okay, I can make a difference. Okay, the difference between this one and this one, and the difference between this one is like this. Well, there are 2 problems with that. In this case, all are positive, so that's okay. But imagine that we got something like a leaky railroad, or something like it's not like this, but like this. So it produces negative numbers. It will be awful if we use something like that, making difference. Because some of those differences will become negative, some are positive, they compensate each other. So at the end, you can get something that is 0 and is completely bad. So a difference is not a good idea. What is the next best thing after that difference? Oh, difference is square. So you have here a square, a square, a square. That is the equation that I put there, is the square. So it's just taking the squares, it will become positive, making a sum. Now I have some of the squares, I take a square root of that. So I am taking like a geometry distance between what I want in 10 dimensions, what I got in 10 dimensions. It's just a distance. There is another way that is loosely inspired on thermodynamics, but yeah, we will not go into that. Is just taking the value that we got, taking the logarithm, multiplying by the value that we got, the value what we want, take the logarithm and making the sum, and the negative, and returning the negative of that sum. In a way, we are undoing what we did with the softmax. On the softmax, we took this exponential with that. We are basically undoing that because we got this things like this. We got a number that is really, really high, and this one are more. This is taking presenting a more rich environment. So they will say, okay, which is the numbers that I really want to push? I know that this is a 3. So I really know that this one here needs to receive a big push up. I know that this one needs a push down. How big is this push down I need? This is what the function is telling. While I select this, it will decide how strong I will moving this down or up when I need it. And this is something that is very often used, the cross entropy function. And the reason for it is called sparse. Okay, and this is just very particular for the way those things are programmed, is that what we have here on the data that we use was, this is a 7, this is an 8, this is a 1, this is a 0. Yeah. So we have a categorical one number here. This is what you call the sparsity of that. If we want to be explicit, mathematically explicit, what we will be doing is creating an array here where we say this is 0, 0, 0, 0, 0, 1, 0, 0, 7, 8, 9. Yeah, something like that. And for this one, we will translate into 0, 1, 0, 0, 0, 0, 0, whatever it is. And this is, if you present the data, the column of labels, this way you put the categorical cross entropy. If you are using the labels with just the number, you use the sparse categorical. That's the difference. It's just a nuance for how those things are presented for the function. Okay, so now let me execute this one here. Okay, I'm just taking this, how that is presented. And I'm computing here this cross entropy function. The reason why it comes called entropy is just because the equation is very similar. You see the equation for entropy. It has some relation with no, what is going? Oh, at some point I forgot to compile this thing. Yeah, I forgot to compile it.
But
yeah,
the matrix of accuracy.
Oh yeah. Okay, let me accuracy. The accuracy is good here. Why? Because we have I don't know, we have 6,000. Well, we have 60,000 sets, right? 60,000, yes. So we have 6,000 zeros 6,000 ones, 6,000 twos, so on and so on. So we had a very balanced situation. So accuracy is a good metric for us to tell us how good we are in this model. I am from a country where this one place in the Pacific Ocean. I'm from Colombia, and Pacific Ocean, one place where it rains 360 days a year. So you can have a model for predicting the climate there. My model is saying, okay, whatever day you give me, I will tell it will rain. My model will be right 360 days during the year. It will be bad 5 days. My accuracy will be very good. My model is worthless. So we have a very unbalanced situation here in this. We cannot use accuracy as a good metric. We can use it here because this is so well prepared. All the images are so nice, centered nicely, and we have the same number for everyone. So
is this accuracy from the confusion matrix?
This is the accuracy that we think when you move the confusion matrix, we have that is the same. The idea with the confusion matrix is making the separation between the things that are right and we predict right, the things that we got wrong and we predict that we say they were no and we predict no, and the things that we predict yes and result no, and the things that we predict no and result yes. And there are different situations where you can feel comfortable with having more false positives or false negatives. Imagine that we are concerned about the COVID. We are happier if we models for detecting people with COVID were such that we tend to say people has COVID if they don't have it, rather than saying people that they don't have it and the result have it, because we are more protective on that at that level. That is the whole thing of that. Here, we are happy with the accuracy. We have this balanced situation with the inputs, so we can say, okay, how good we are with each number in general. Okay, so here I have this in this non-categorical way, just to show you how a phi looks like in a non-categorical way, an explicit vector where we say from which one, a 0 for the non-belong to the category, 1 for the belong to the category. As usual in NumPy, we index from 0. So this is 0, 1, 2, 3, 4, 5. This is how we declare that. So here I'm applying this softmax. We got this value here for the log of the softmax. And we are getting this value here at the end. So this is what is happening. So now the fitting of the model. So we compile the model, and now I will be fit. This is the important part. This is what all the time, this is why we need a cluster. You start seeing this kind of messages, you see, this is typically from TensorFlow. You get this message. Let's see. There is one word here, epoch. This is how many times we are presenting the type data set to the network. The network is taking all, is flashing all, and changing the weights in such a way that the next time it becomes better and better and better. How we know that they are becoming better? Let's see the first time. After the first cycle, it got 0.89. This is a very simple problem. And we have too many parameters. So it goes really 89% good for the data that we present. The loss is the value of the loss function. The way we define the loss function is that value. Now, after we are presenting here validation data. Is this tiny data that we are not using for training? So we are not presenting that data for changing the weights. We are presenting the data to see how good we are with things that are out of the sea of the training. So you see always you get a lower value here. Or well, at the very beginning you see. So here we get 94, but that's just because it's the very beginning of this. You will see after we are, how many I did run here? I run 20 here. So I got 99.6 for the data that it was used to training, 97.62 for the data that was not used during the training. So you will see this is okay. This is much better when you see this in a plot. Yeah.
And the initial values for the parameters were random?
Yeah. Random. Yeah, they are random for two reasons. One, if you put zeros, it will be, it will. Also, when you put zeros or you put something very symmetric, very symmetric, it will start fighting or will be not learning. They will be just fighting back the symmetries. So symmetries are very good. And we will see that symmetry is the guiding principle in physics, at least for the 20th century, is super central for physics for many areas. But this is one of those cases when we don't want to use symmetry at the very beginning. No, it's random. And we see here, the blue is how it's improving the weights, all those weights biases, all those 55,000 things are changing, are giving us better answers. But we also see that at some point, it is giving good answers for the data that was used for the training, but not so good answers for the data that has not been used for during the training. So this difference here is an idea of how much is remembering the data, remembering the inputs to the outputs rather than learning. How much are you losing in abstraction in the process? And you see, and this is why I would like to make this very evident. It's you got this the best that it could for this after the epoch number 5, maybe. The validation data was not the accuracy on the validation data was not improving after, let's say, epoch number 5 or 6. It's flat, they have some bumps, sometimes it will go even lower than that. So we are not doing better. So I run this for 20 epochs and I wasting 15. And this is something, and this is the importance of this kind of workshops, because I see many people who are using our cluster for this, who are doing this all the time. They're running because they want, and if you see the validation data, it's improving after the very beginning. So this is the best after 5 epochs. This is the best that this kind of neural network can give us. It will not be better than that. So all that has a specific term in machine learning. It's called overfitting. So overfitting is remembering versus learning. It's non-abstracting the thing. Also, another way of putting it is with the loss function. And I am plotting this on purpose on a log scale, semi-log. So you see, after around 4, 5, you see the loss function, which is the function that is telling us what I put here, how bad we are. for the training data is going better and better and better and getting very, very tiny loss functions. But for the data that has not been used, it's not so good. It saturates and it's going flat at some point. So now, what we can do with this? This is the next part. It's, wow, we'll go, Rich. Well, I will present this and I will probably will regain this tomorrow. And so 5 minutes. So I would like you to present this, to see this. If you want to run this, I will be doing this again tomorrow. Thicker networks, I am making this with more values. You can see there, you can run this section, and you will see what you get. In the meantime, I will run it the whole network here. So just to show you the event, so you get like an appetizer of what we will be showing tomorrow, our point of entrance for tomorrow. Making this bigger. How bad? Bigger. Is bigger better? Next thing, is deeper better? Putting more layers. So on the next example that I have there, I am putting here 64, 64, 64, 64, and 10, and 5. And after that, I will show you the next, the best solution, or the solution for that, that is called a convolution. The convolution, who was the big thing, they made the headlines on this. So a convolutional neural network, which is a different way of putting the weights and putting the operation in place. And I was using a simple here convolution, a max pool, like a reduction, like a zooming. We will see that in detail, and after a flying prediction and what we get. And after I am putting more layers of convolution, we will explain that tomorrow, and adding dropouts. Dropouts is something that is kind of counterintuitive, is cutting networks at random during the training. Cut here, I'm cutting 25%, cut and use, and when the next time arrives, it cuts differently. So it's a little bit like making the network drunk, and somehow that makes that perform better. But so you see, and you see, it's still, well, it takes a while because I'm running this on a CPU. And at the end, and this is for tomorrow, you will see that this kind of neural networks reaches a limit what they can do for these kind of problems. Those dense networks, you can bigger is not better, deeper is not better. So now you change to a convolution. A convolution works much better than those dense. We put more layers, it works better. We add dropouts, it works much better. So we get a very, very high % of success and accuracy on this set. And this is the final point of this. Tomorrow we will be presenting this with a faster pace. I hope you get the idea of how to use the notebooks. Use the notebooks, run those, at least the first notebooks. Tomorrow I will be entering with this one. Training, no, not training, using pre-trained networks that will help you to identify a photo, the animal on a photo, and after a network that converts horses into zebras, so which is a cool thing to show you a very special kind of network. Well, probably not much scientific, but purpose, but is something that enlightens you to be motivated to learn this. And after we will go back and relearn in more detail all the math, matrix multiplications, the ReLU, the activation functions, all the so it's another pass on the team more on convolutions, and machine learning in the afternoon. So this afternoon, pure Python, no general focus on machine learning. So what you need to learn in order to be effective on deep learning, but I will not be mentioning machine learning. I know what you need to know, and this is what I'm putting a focus on. Functional programming, the ITER tools, the right things that are widely used in machine learning, widely used in this context, NumPy, and you feel better prepared to see those notebooks and understand what they are doing. So for this afternoon, Python, with a focus, with a light on deep learning, not mentioning deep learning. Thank you very much. I will stop for here. We return at 2 o'clock. Okay. Or Red Hat something running here. So I will be entering the commands of a Linux machine on something that is running a different kernel. The kernel of a Mac is a derivation of something called Darwin, and that is a derivation of something BSD. So it's an old-fashioned Unix thing that had been diverged over the years, but at the bottom of this is still the Unix machine. So same thing here, you are running on a machine that it's running Red Hat 7. This is a very particular distribution of Linux, but you can have an image that was prepared with the file system of an Ubuntu machine, something that is probably more popular for people in the academia, for example, that we are using Linux machines for them as desktops, so they use Ubuntu, it's more familiar. So we can have an Ubuntu file system embedded on a file, and when you run on a Red Hat machine, you will be opening the file system of Ubuntu. You can have the commands, and you have apt-get, the typical commands for installing packages. You can install those packages on the image. So you can all have all that, and vice versa. You can have a Red Hat machine running on top of a Ubuntu machine, or a different version of a Ubuntu machine. So this is something that is very good. For example, when you are in the industry, you have web servers, databases, and they are running on containerized. So when something bad happens, they just delete that, put another image. It's a software thing. So you continue to run, and every second could be a lot of money. So you keep all those things popping and moving up and down. So that is, for us, is Singularity. The solution is Singularity. It's a containerization solution for HPC systems. So that's what we are using, and we have here. So you can see here, if you're curious, we have a lot of images here with TensorFlow, Python, and those NGC. Right? Do you see here NGC? Those are NVIDIA optimized images for a specific tasks that are particular well suited for GPU usage. So molecular dynamics in chemistry is something that takes advantage a lot of GPUs, and deep learning is what you see all those. So MXNet is here, and I have a very, very recent versions of that. So those were the versions that have just appeared a few weeks ago, so they are fresh, all of them. We have 2 versions of TensorFlow. Probably this one is not working, but it's something I need to fix. Okay, so that is, move on. So optimizing, we want a code. The good thing about Python is that you can write code quickly, easy to see, easy to program, very intuitive. It's not performing particularly great. But with some things, special libraries, special tweakings here and there, you can get better and better. So you can start competing with low-level languages like C, Fortran, which are really, really close to the machine. So what is your role here? Let's say as a scientist. Well, so your role here, if you're doing a PhD, is to publish papers. And to publish papers, you need to write or programs or use programs from others and write scripts to automatize things, because otherwise you become a monkey doing over and over and over to the next 4 years exactly the same thing to get your paper done. Or you automatize things, you can, instead of having just one paper, you have 2 or 3. So there is those roles between being a programmer. So you are writing a code, you are really developing something out of nothing, or you are just making a scripts like dirty codes that will run, will automatize something, you get the things done and you won't. Those are valid ways of using Python. They're very, very good at that, especially because you can run those things in an interactive job. So you can have, for example, here, all your analysis, statistical analysis, working on a notebook, you can present to your PI, okay, I got this, they can check. They say, no, this one is not, you change this parameter. So, oh, no, you change the parameter quickly, you run, okay, here is the data. And you get the plots look nice with Matplotlib, you can get those publishable, so they look nice for publication. So you have an environment that looks good and is properly well suited for scientific purposes. So how we start this? We'll start from the very beginning. This looks like a calculator, so you can start doing math, typically math, perfectly fine. You can also do things like this. So this is a very, very compact way. You see how compact the language could be. I don't expect you to understand this box. I will explain the details on this box. So you can, okay, here you did some math. This is okay. So you can use this thing as a calculator. That's great. Now here you can have something like, yeah, like list comprehensions, so for loops without explicitly presenting the loops. Not. So very, very compact ways of doing that. That's the objective of this, that we are able to do that. I will present this example of how compact the language is and at the same time expressive. And so this is a very, very classical algorithm for sorting. People in computer science learn this by heart, the quick sort. So how this looks from Python. And this is the same version of this code. Well, they're doing exactly the same, but this time in C. So you see, you have to put more things, more loops, more conditional, more things that are really, really compact in Python. You are forced to be more explicit on that. And it will be very similar with some advantages if you go into Fortran, because Fortran is very good for arrays. So eventually you can reframe a few things slightly. There are today there is just one version of Python, Python 3. Forget about Python 2. If someone give you a code in Python, we have Python 3. Python 2 has been no longer maintained since 2020. So we can consider Python 2 something that pre-COVID era, so too old. So everything that we are doing is using Python 3, especially some things that I will be doing are Python 3.6, which is now old. So let's say this notebook should be running fine in Python 3.7, 3.8, 3.9, 3.10. And there are tiny little difference with those, but nothing so significant as the difference that we have between Python 2, something on Python 3. You can get the version that you are using by from the command line. If you are on a terminal, you can execute this command, Python --version. If you are inside IPython and Python interpreter, you can do something like this. So I'm using this version, which is compiled in June 11, 22. That is the version. There is a very recent version actually. Variables. So before that, constants. You can print things here, text. So you can put those texts with quotation marks. Quotation marks, you can put it single quotes, double quotes, it's okay. So you can use single quotes to put something that has double quotes inside, or put single quotes with something that has double quotes inside. It would work that way. You can put comments when you start with the line. Everything after a sharp is a comment, so you can skip that. Variables, This is a soft typing language, so you can define a variable with something, you move on, and you can change it. So I am defining several kinds of variables. In a computer, it is important you separate something that is integer from something that is a floating point number, which is a real number truncated. The computers are not capable of storing real numbers. There are too many, they are infinite. And so we truncate them. And that's the way you can store complex numbers, strings and booleans, so true and false. And you can do small things like that. So there are a few words that you cannot use in the language because they belong to the language itself. So this is the list of languages of words that you can use. You can define variables like this, like this, like this, and well, I put here again this one. So notice that when you see, okay, I need to define a variable, you check this place for the exercises, and you will see. So numbers 3, you can make addition, subtraction, it's okay. You can increment or multiply like this. You can, what I'm doing here? Okay, yes. Still, when you define a variable, the final receives a type. You can check which type it has. If you can take that variable and define some other variable, and it will change the type automatically. So here I'm checking the type of y. Y was 2.5. So this is what I'm returning here. What else? What else? We can move on. Okay. What I'm doing, this is, okay, the precedence of mathematical operations, the PETMAS is something. There are different names for this thing. In England it's different, probably in India it's different, but we use, well, you see, parentheses, exponent division. There are small subtleties with those things. So booleans can work like that, comparisons, true or false, strings. I mentioned this, single quotes, double quotes, they were just fine. And you can get the length of a string using this. This is something that eventually could be important for, I don't know, this is one notebook where you are making some things with strings. We can keep this. This is one way. I will present down below another ways of filling variables into a string. This is the old-fashioned way with this operator. This is not the only one. It's just the old-fashioned way. So this is what I'm doing here. You can take the strings and change the casing. So put something and capitalize, put the first letter uppercase, move everything upper, lower. So strings work like this. So you see an example of a string. You can access the different elements of the string with a number, with an index. 0 is always the first index. So 0, for example, if you have a string that is Monty Python here, so 0 will be the M. This is a convention in Python, everything starts from 0. Also, you can ask for the last element using this indexing with -1. This again, we'll reiterate this when you start working with NumPy at the very end of this session. This is important. So you can have the different letters here going from 0 to n-1, or going from n-1 to -n. So that is, you can get portions of a string using this slicing convention. You put the element that you will be using for storing and the number after that. So the quick mnemonic trick to know how big this string is, you just take the subtraction of these numbers. 10 minus 6 is equal 4. So you are getting a string of 4 digits, 4 characters. This is the quick thing. So you can always compute that and get an idea. So this 6 to 10 is not including the element number 10. It's just 6, 8, 7, 8, and 9. this is how the strings are captured, superstrings are captured. What I'm doing here, well, other ways of saying all that, taking strings, the string format, well, probably this is the thing that I told you. So you can print, this is especially for notebooks, when you need an print things, you can just put print in the notebook, you just put the variable and it will print if that's the only thing in the box. But yes, you have the command print to print on the text. There is a similar command for storing data on files, on text files. Okay, so I am storing here files. So ways of storing of formatting strings. This is kind of actually something that contradicts one of when you see. I passed that very quickly. The scene of the zen of Python is that we should have one only way of doing things. Well, here we have four. And the thing is that, well, you need to know the rules before knowing how to violate them. And this is pretty much what is happening here. So we have, at the end, we have four ways of putting strings in place. This is the old-fashioned way. You just use this operator to change the variable according to the digit that we put in front. So you are replacing something that is a string of characters, you put S, and enter D and F for floating point numbers, and some others that are less commonly used. Here I have some examples doing that, where I have here 4D, for example, here I'm using 4D, so I'm putting, and by the way, the 4 is meant to say, okay, I will be printing an integer, and I will be separating 4 spaces for that integer. So that's the idea. Here, when you are doing this with a floating point number, is you are saying, okay, I need 6 spaces for my number, so we'll make that 6 spaces, and I will be using 4 spaces for the decimals, which will give me just 1 extra decimal for one extra space character for the dot, 1 number, and I will not be able to properly print this if the number is negative. So pay attention to those things. This could be problematic, and so that's why I put it there. Strings is this. So this is a way of something when you want to do something nice, and you want a table, and you want the numbers to be well aligned, and don't have it like a zigzag of numbers. This is one way properly formatting those things. So this is one way. The new way is using this from Python 3. So you put just these curly brackets, and after dot, like an operator, we will see with how that works with classes. So we are taking an object, which is a string, we are applying a method format to put elements there. In this case, a name inside. This is the new way, and you can also put here inside the brackets like a name for that, and you can map those names inside the format here. And the reason why this was popular and still widely used is because this is very, very close and the way you program that in C. Yes, and even in Python, even in Fortran, you use something like this. So those things come from Fortran, and those or something very similar to this. And this one is a modern way of formatting strings. So for something that really Python 3 typically would tend to use this one. This is a new format that I will be using some of the deep learning notebooks. But this is a specific for Python 3.6, which is now also it's okay to use that. You just use this F on the front of that, F, and the string with quotation marks. And here inside, you can put variables, you can make operations, you can do things inside there. So it will be closer. You can do operations closer where the data will be inserted. It could be convenient. That's the reason why people create this other format of doing it. So this is something that I do here and here. So this is the third way of formatting strings. And there is another way using the standard library, something that we will be in the next notebook, that with substitutions. So we'll see that. Okay, we covered really quickly the first part, variables and strings and all that. Let's move to the next part. 30 minutes, great. So again, this is fast-paced. Idea is that in the afternoon, later, you open the notebook and you see with the right curve and absorption. That is where you learn. Learning this with curve. So list. So now you see one variable, but for example, in deep learning, we are not working with just one variable. We are working, you saw here, 55,000 variables actually. So there are better ways of storing variables that are massive. When they are not so massive, you can still work with something like lists. This is basically a way of storing data with one variable, and you can index different elements inside that sequence bind. And this is how you create a list. I'm creating a few elements here. By the way, this list, each of them will be in different places in memory, different sizes. You can put more, you can put a list and add variables. You can take variables from the list. It's very flexible, but that flexibility comes with a penalty in terms of efficiency. So this is not the way we program neural networks. Never. So it's just for storing reasonable amount of data with lists, something that is just a few hundred, maybe thousands, but not more than that. There are better ways of storing data. You can create lists of lists, and those could become eventually using other tools, matrices, arrays, multi-dimensional arrays. Those things that we were using here for the images, it's all bunch of images, and each image is 28 times 28. If you are dummy enough, or you don't know what else to do, you can think about a list that contains a list that contains a list, and work with that with 3 levels of insertion of listing. Again, not something that you want to use. Slicing. So again, same thing with the same idea which we use for variables. There are ways to index in particular elements, or you can take a portion of the elements of the list, and that is with the slicing. Same idea. You want to know how many elements are from in this expression 2 to 4. You just make the subtraction. There are 2 elements here. It will be the 3rd element and the 4th element, because we start from 0. So 0, no. 1, no. 2, and 3. And 4 is not included. So that is what we're doing here. What I'm doing here is a range. So I am making 5 numbers from 0 to 4. Ranges in Python 3 are not lists. They are iterators. So we need to convert that into a list to make it explicit. So that's what I'm doing here. And later on, you can see, devote some time to understand what is happening with those slicings, how we take portions of that. You can run. This is how we will see that in a minute, the running loops. So this loop is something that you can use, for example, when you are iterating over the elements of the list. So here I have all the Platonic names of the Platonic solids here, and I would like to print them all. So each one of them is taking the value, printing, taking the next one, printing. What else here? So I am here, I am doing an iteration here. With, again, the idea, we will see this in a minute, to put in the index and put that like a list with a numerator. Okay, copy list. You can create empty list. Again, this is something very flexible. It's something that you can create out of nothing, start adding elements, taking elements out, moving, adding and deleting. So here, for example, I am appending one value. We create an empty list and I put another one here. I am doing a change here and you will see that I change here to this list called M, another element, but also both lists end up having the same value. Pay attention, devote 3 or 4 seconds so you understand what is happening here. So when you execute this, this is not a copy in the sense that no memory has been duplicated and separated. It's just a reference to the same object. If you change one, you are changing the other. This is something that happens with lists, and is happening even more when we move into NumPy arrays, which are crucial for deep learning. So that's something to pay attention. Why are we doing this? Is because we need to save memory. Memory is very precious for us. So especially when you are doing with 55,000 things, you don't want to start copying it. This is a very small network we'll show you today. So if you see the list of those neural networks that are one of the networks that we will be working tomorrow, the pre-trained network, they have 14 million parameters, 14 million. And that is still very small for today's standards. This is a network that was hot topical, let's say 5 years ago. And today is easily in the terms of billions of parameters. So that grows very quickly and you will not be able to move the data, make a copy of 20 billion parameters to do something. So those things are just references. So you can manipulate them without making copies. Also another thing that will be showing you here, so you get later on a better grasp of this when you run on your own pace, is the idea when you are copying those things, you can make copies of those, but still the objects that are inside those are not copies. So those are called shallow copies. And there are procedures where you can copy the elements and properly copy the elements of those elements. So you get really a copy of that. So there are some subtleness on the management of a copy. And this is the description a little bit of the difference between making a shallow copy or making a deep copy. So really separating the memory locations of the when you spread that properly. So this is a deep copy using something that is in the standard library, something that we mentioned. You can delete lists, you can remove them from the memory. Here I am probably deleting elements from the list, doing a few things there. You can sort the list. So sort is a property of the list. In the case of strings, they are sorted alphabetically, numbers are sorted, of course, the number. And this is the thing that I mentioned, that I showed you at the very beginning, so you get an idea. So you can create these lists with loops where you are adding elements, but there are better ways of doing things like this, and they are called list comprehensions. So in one line, so with one-liners, you can achieve those results very quickly. So when you see, this is something that happens a lot in deep learning, in the notebooks that we will be working, this becomes second nature to you, manipulating those list comprehensions. They are very short, expressive, clean, and there are ways also to create, probably here, dictionary comprehensions, not so often used. So, okay, dictionaries. So now we have a list of values. So we know, okay, we have a sequence of values, so we can address those one by one with an index, or we can take just a subset of them with the slicing. All those things work perfectly fine. So now there is another way of storing data. It's called dictionaries. With dictionaries, we are attaching a key to a value, and dictionaries could have a key which value is another dictionary, and put again those things like in a tree or something like that. This is another way of storing data. Again, works fine when you have 100 elements, was reasonable when you have a few thousand. Beyond that, it's just madness. So there are better ways of doing these kind of things. There is a point where efficiency will prevent you from scaling this to much further. They follow basically the same rules of list. You can take one element, remove them. What I'm doing here, okay, so I'm taking the value, the key and the value, and I'm using that to print in a list. Okay, how many faces each of those platonic solids have, and dictionary comprehensions. So you see, so now we're building the language, and also we are building the tools, especially the tools that will be often used in deep learning, in machine learning in general, and in scientific programming. Python is one of the best languages for scientific programming. As I mentioned before, for the high tree. Another one is sets. So in this case, they have no order, no repetition, so you can have something like this. So this is another object that we manipulate a set. Probably miss tuples here, or maybe not. Oh, will be maybe it's later. Okay. So here we can use that for looping, for enumerating. The enumerator will put a number and the elements, so we can work with them. So okay, tuples. Okay, tuples are right here. So those are especially we use. For example, we are in a space, and we know that we will be storing 3 values, X, Y, and Z. So with a tuple, we have those. We know that we will not grow those for more than 3 elements. So that is how we often use those things. Arrays that will not change in this sense. So now, now the language. So what you want to do, this kind of languages are called imperative languages. It means that you are explicitly saying what to do, not just declaring what you are expecting from them to get. So those are, let's say, nuances in computer science. But the point is that all those languages that I mentioned to you, Fortran C, C++, the low tree, and the high tree, Julia, Python, and R, all of them rely on this kind of things, conditionals and loops. So the way the program works is that they follow a logic where something could happen, it will go in this way, something is not like that, no condition will go into another way, something could go, all those themes are there with different declarations, but they work. So for that, before having conditionals, the important is how to say if something is false or true, because that is how conditional work. So I'm declaring here how you make process a conditional sentence here, and how we use the else conditional in Python. So one example of this. One example of the if else. So it will be taking if, something that should return true or false. And if it's true, we'll be doing this. If not, it will go into the next one. And if you have an else, it will go into that clause. And notice that here it will be entering just in one of those options. It will not continue to try this if already succeed with this one. So that is something very important here. More loops. So we typically, there's this one, while more elements here. So here you are having something that is changing. For example, the X, I'm increasing the value X and iterating until the conditional returns false. So it will escape out of that loop. Okay, here. Okay, with multiple lists, this is something a little bit more elaborated when we are taking elements from two lists. So we are taking like in pairs of them. Ranges, I told you this in Python 3, it was not the case in Python 2, and they return an iterator. So to convert them in list, you need to be explicit to convert them in list. And this is important when we start doing the functional programming, which is very strongly connected to neural networks. The iterators, all that is right on top of that. And here we have ways of we are doing a loop, something iterative, and we want under some circumstances to escape of the loop. So there are a few ways of doing that. The break will just escape you the loop entirely, and the continue will just move into the next iteration of that. Okay, so that is really, really fast paced into variables, containers of data, sequences, loop, conditionals, loops, and now we are very decent because I want to concentrate on NumPy, which is what really important. Functions. So here you can declare functions, math, and then we will see this in a minute. This is part of the standard library, which we will comment in a minute. That how you do some math. Well, this one is, for example, showing the calendar. Okay. Function external modules. Okay, so this is something. Now, after that, you can define functions. So this is how you define a function with def. Here, and this is something that I forgot, it's super important. And notice that in this language, there are no open brackets, closing brackets, if you are familiar with C or Fortran. Closing and open and closing. The opening and closing is just derived from the indentation. This is like a byproduct, a very modern way of programming, is that indentation became important here in this language. And this is one thing where you strikingly see the role of the indentation. You define a function here, so something that you will be using later on, and you just make an indentation. So you need to be careful. The size of the indentation is just an aesthetic matter. But the fact that you need an indentation is central. And so here I am defining a function here, and we will be defining functions everywhere in the deep learning, especially with some ways of building those networks is really evident. So here I have an example. I will be moving quickly over this. This is more for you to read later on. Basically, what I'm doing is creating a function that produces the Fibonacci sequence. So here, so I am taking the range, I am doing the operation, showing you how this sequence works is something that is part of nature. And here is the way of producing the Fibonacci with a function that calls itself. So this is kind of neat. The way this you can make a function that calls itself to produce a result, perfectly legitimate in Python. And this is how you work. So what I'm doing here, I am showing you two ways of doing this, and showing you this with the proper changes. There is a huge difference in the performance of one way of using a function compared with another way of using a function. So this one is, for example, the fact that I'm using the recursive or the fast trick. So you can read it. Other alternative ways of declaring functions. The important thing is you need to know that how functions are declared, and if you have time to concentrate on a little bit of the details of what I'm doing there. And so, yes. By the way, this is a way of plotting functions in Python. It's really simple. There is a plot, and here I'm using another version that is called the semi-log y. So it's linear in the x direction, is semi-log is log in the y direction. You put just the arrays that will go into well, if you put just a list of numbers, it will just put it will assume that the indices will be x-axis. We will be plotting a lot for the accuracies, losses, all that. So you saw this morning. Functional programming. So functional programming is super important in machine learning, in deep learning in particular. The fact that we have functions that we it's like another way of thinking about programming. Here, the central role is a function that has a state, so you can have a function, calling another function, and the output of that function getting into the input and on the next function. So it's something that fits really nice with this schema way of thinking. So you have an input, goes into a function, which is this rotation plus translation, that goes into a function that is the ReLU, the activation function, and after that, the output goes into another function and another function. So that is something that happens a lot here. So here, one function that is one way of programming that is particularly important is this way of declaring functions that are so simple that doesn't deserve even a name. So just take something and return. This is called a lambda function. Basically, I'm taking 3 values here, and I'm putting a name here. But this is function. It's so simple that I can create it with 1 line, and it will operate. I am entering the value, and let's see, and it's taking the operation. So. And so here, for example, I am making another where I am having like a string. I know that there are a column in the middle, so I'm just splitting with a string. I think it's up there that you can split a string with a certain character. It will be 2 elements, so you can take the first one, do something, take the second one, do something. So yeah. So something that I will be elaborating a little bit more about functional programming in the next notebook. Let's move into object-oriented programming. So here the idea is to have object-oriented programming and functional programming, kind of the completely opposite phases of the programming idea. So here we have a function with variables, and those functions and variables are kind of tied together. So you have properties and methods that work on those properties. A lot of those frameworks, PyTorch, work on top of classes. So when you are making complex networks, you are overloading, you are extending classes all the time. So that's why knowing this is important, at least for this part, knowing that there is on a special method, that's the terminology here. So we have a class. So a class is something that has variables, so properties like the color, height, age, something like that, and functions that will operate with those variables. There is one method that is crucial for a class, and is the constructor, and is this one that is underscore init underscore. And when we build with some networks a little bit more complex, we overload, we extend another library and model library, and we change this constructor for building. So pay attention is this, when you see this, you just see, okay, this is something that is from object-oriented programming, this is the constructor, so you get a little bit of the feeling. And we will be changing another one for the model here. So we will be changing a few of those methods for building networks with PyTorch. I'm doing this, so here, and here, how I create an object of the class. That's the name of that. And creating objects. The objects will be instances, will be realizations of the object. The object is this abstraction, this thing that could change faces, could change the realization. It will be a particular instance of that. So one thing is your abstraction of a dog, another is your actual pet, which is an instance of that abstraction. It will have the properties associated to it. Okay, here I have one example, super fast. Yes, exactly over an hour for the first notebook. This is using class for an special mathematical object that are called quaternions. So this is like an extension of the complex numbers. We have quaternions, we have octonions, we have sextillions, and they have their own ways of operating, and they have applications in when you are dealing with rotations. There are better ways of presenting those. Some people, and they're probably familiar with manipulating quaternions. I am just using this as an excuse to create an object that is capable of manipulating quaternions. I will be rushing a little bit on this part, so you can take the notebook and read it in detail how those quaternions are. By the way, the trick here is that this object, those mathematical entities, they have like a multiplication table. So if the element is y times y, so the same element will return a real number. When they have different orders, so they return in a cyclic way. They have a lot of uses. So we will see. Skipping here. Okay. And I will be doing this. This one is something that is it has a role in deep learning, the decorators in classes. So there are like tiny little strings that you put on top of a class to get some effects. Let's see if we can find one here. But I think we can skip that. Okay. There are some static methods and class methods. Yes, we will see that when we see this in due time in the deep learning. That will be more clear. Let's say, rather than rushing here, you will it's something that you can put here, and this method can be used out of a specific instance of the class. So you don't need a specific dog to have something like a function that will operate regardless of the dog. It's very attached to the dog, but you can you can use it without the instance. That is a class method, by the way. Sorry, this is a class method. So well, we'll skip this. So we'll move into the next, which is really, really important. Abstract method. So I will this. So what you should keep in mind is that classes are variables with methods, with functions, all together. And so they are close together, the functions and the properties. For example, look at my typical example, especially for a kid, are those in games. So you can see those games, you have a lot of I don't know, farmers or soldiers. Every tiny soldier is just an instance of an object, of the general object, which is the soldier. The soldier will have some properties like the sword. What is the quality? And the sword is also an object. What is the quality of the sword? So which are the properties? How much life it takes when it hits the enemy? So also each soldier, well, they have a property which is the color of the clothing. But each color, so they will have that variable associated to the instance of the object. And when the computer is drawing all that, is looking at this, okay, this is a soldier. So how is the color? Okay, the color is this variable here. I will take that. I will search for how is the way you present that element for the game. So the clothing belongs to this team or the other team. It will be red, it will be blue. It's capable of attacking, all those properties. So this programming for games, it fits really, really close into the idea of object programming, object-oriented programming. So I'm here doing another one with Platonic solids, with classes. So probably this is less and less relevant, just for you to keep in mind that the Python 2 was something that exists until before the COVID-19. So pre-pandemic, nobody uses anymore. It should be something for the old times. But still, you get surprised when someone arrives and say, oh, but my professor told me that I have to use this code, because what was the code that he was using when he was doing the PhD? And that code is written in Python. So, okay, so good luck. So that is another thing with X-range. Okay. Something that is not good anymore. I put here something like an exploration of those differences. So now, through scientific computing. I made a selection of a few packages that I widely use in scientific computing. Apart from specific from the learning in general, the central one, the de facto standard for manipulating large amounts of numbers in Python is called NumPy. Actually, it's the PySpark. Anyway, so here, okay, you can use it for 2 times 2 matrix, but this is really, really shining when you are manipulating huge arrays with those that we saw here in deep learning. So we will be working on that. I am rushing on this because I would like to put emphasis on the NumPy because it's central to deep learning. So this is just the quick introduction that this exists. Everything, almost everything in scientific computing is built with Python is built on top of this, on top of NumPy. So you should really, really understand how this thing works. And each deep learning framework basically make a copy of the way of this thing work with the extra capability of storing that on GPUs. So NumPy is restricted to storing that on CPUs, but deep learning is mostly happening with GPUs. So PyTorch, they have torch tensors, which behave like NumPy arrays. MXNet, they have the ND array object, which behaves like the NumPy. And if you go low level with TensorFlow, you will be working with TensorFlow tensors, which work really, really close to how NumPy works. So the slicing, all that works very, very similar. So that's important, understanding NumPy and later understanding the small nuances of the other. SciPy. SciPy is a central package for, let's say, numerical operations that a scientist typically do, like numerical integration is one thing. Optimization, so finding the roots of a function with methods that offer the gradient, methods that often offer more than the gradient, so you get Jacobians, Hessians, all that. So you get some extra spices to get better things. So all that manipulation is something that SciPy can give you to you. Special functions, Bessels, all that. Yeah, I skipped this one. I skipped this one. So yeah, so here I am introducing what I'm doing here. Okay, and a special function, which is a Bessel function. So okay. Matplotlib is the de facto standard for plotting on, especially 2D plotting on Python. It's like the equivalent of ggplot on R for those who are familiar with that language. So you have ggplot there for R. We have here NumPy, Matplotlib on this side. So I just made an example. We will be using this, especially for plotting the accuracies and losses. So, but you can also plot some 3D stuff. They look nice. SciPy, I was probably doing something with SciPy. This is for symbolic manipulation. And I don't know how far they have gone into this route. When I was on very theoretical physics, and high energy physics, I used to work with Mathematica because it was much better at that time. I don't know if they have catching up on the functionality on this one. Just to tell you that at least yeah, this was something that you can use in Python. So another good thing is that at least in NumPy and in notebooks, you get the equations transferring to LaTeX, and from there they will use the capabilities behind Jupyter notebooks to express those nicely from LaTeX. So that is okay. And so here, unimportant. Okay, another one. The final one is Pandas. Pandas is a library for data analysis. And the central object in data analysis are tables, which are called data frames, which is basically like Excel tables, when you have a column with dates, another column with numbers, another column with names. And so the columns have different types, which is something that you cannot have on a NumPy array. And they have ways of moving things from NumPy arrays into pandas and going back under some circumstances. But this is really a library for for working with data frames, with tables, especially when those tables are ugly and dirty. So they have missing values. You have nans, like not a number, things like that. They have functionality to clean data really efficiently. This is something that I'm taking. Those are human indicators from all the countries in the world for many years. So that I took a few years ago. So you see many countries, more countries, and I was just taking some data from one country, for example. So you can play with this, try to get your favorite country and get some data from it. And also plugin. So they connect behind curtains with Matplotlib, so you can take one data set, one column, and plot it versus another column. This is something. If you are working with something that resembles these kind of things, this is one library that you should consider. If you go beyond what you can do with pandas in terms of really a lot of data, which is called big data. So when you can no longer process this with a single computer, you need to move into a different solution. And I present the workshop of last year was on that, was on something called Spark, which is a big data solution that does a lot of things that Pandas is capable of doing, but this time even using many cores, many computers eventually. This one is the closing of this one. So I have my leaves here. So that's it. Let's go this one here for the next library, and I will be completing this quickly, and we will pause for 5-10 minutes, and after I will present you NumPy. So that is what I really want to devote at least 30 minutes. So the standard library, they have many modules. I am just selecting those modules that are mostly relevant for us in machine learning, deep learning, that we will really use, period. Yeah, everything else you can move and see on yourself. So I made a selection of those. They are called a standard library because no matter which implementation of Python you have, they will be there. No matter on which machine you are working, those are there. With some exceptions, they work exactly the same. There are things that only works on Windows machines, or something only works on Unix machines that for those modules. But for the large majority, this is an abstraction that works well consistently no matter what. And that is called the standard library. And this is part of the things that give Python a lot of power. So not reinventing the wheel. Sys is one of them. So we saw this, how to get the version of Python. They have also some things for looking into how many bits you are using for data types internal in Python. So this is one library, Sys. We use it for that. We use it if you are programming a script, not something in a notebook, like a script when you are getting data from the command line. So process this, and you, for example, the number of hidden layers is something that you want to provide here as an argument. So, and then here, build me a network with n layers when n is something that the user will give me. It's something that you can use with Sys. If you want to go better than that, there is something called argparse to getting the data from the command line. Those are the standard. And there is this one, math and CMath for basic operations like square roots, cosinos, all that for real numbers and complex. This one is central. Pay attention to this one. It's OS and OSPAD. It's everything that you need to manipulate files and folders on the system. You use OS. Variables, we use this one for some variables that I need to change so the notebooks work correctly. I need to do that in some of the notebooks. You can create and delete. So I'm doing this when I am creating a network like this. You will like to store the weights at the end or during, at least at the end, you want to store the end, which is actually your machine. Is the precious thing, are all the ways that do the right thing. So you want to store them. There are ways on each framework to store that data. So at the end, I was deleting that, creating folders. So you can have like a collection of weights and try to test them for different purposes. So that's something. You can check if a folder exists or file exists, delete. This is a generalization of OS. This gives you more power so you can delete entire trees. So the contents of a folder on everything that is inside it. For that, you use shutil. This one is very particular for functional programming, ITER tools. And notice what we are doing here. We will see more of this tomorrow, that when we are doing the back propagation, we are paying attention to the weight, to the derivatives of this one, with partial derivative of this one, related to the weight here, or related to the weight here, when everything of course will become constant. So all those partial derivatives, they open, they expand. It's all the combinations that you can do here that connect this point to this point, this neuron to this network, to this neuron. And those are iterators. So this library, for example, is offering something like that. You can create iterators, things that just give you new values every single time that you ask for the next one. There are ways to create final iterators, but the really shiny thing are something like this that will resemble what we are doing here, where we are making all the permutations, for example, of A, B, C, D. So notice we are connecting those networks inside and inside and inside. So we are connecting one neuron, communicating the data to another network, and this one we connect to another. So that's how that grows. Combinations. So here I'm doing the permutation combinations and also the product, the set product here. This library, this is often used in machine learning, but less on deep learning itself. This is a way, let's say, put it this way. This is a way of storing with a standard format a dictionary. It looks like a dictionary with some small changes. It is a way of storing structured data in the way where you have the data and the metadata nicely encapsulated. So that is a little bit like what I'm doing here. This looks like a dictionary, a Python dictionary, and the format for this is standard, and you can use this with JavaScript. So if you see, and if you go into this, this is what D3GS. Let me see if I'm. This is something that show you, for example, this is a way of computing with the web interface. It's really nice. Voronoi cells. So yeah, now we're not going to explain it all. This is really simple. All behind these things are JSON files. It contains the points and how this works behind. So JSON is something that is really used on that level. I'm saying that not so much for Python, because for deep learning, sorry, because typically what we use for deep learning for storing the weights here, which are NumPy arrays, is that we store that usually with HDF5 format or pickles. This is pickle is a very Python specific way of storing a large amount of data. And HDF5 is a standard library for storing hierarchically massive amount of data. So those solutions are more often used. Subprocess is something when you want to execute something from the terminal on the machine. Not so much for machine learning, for deep learning in particular. And multiprocessing, I have just one example here where I have a worker, and right here. So I am loading a worker, so a function, and I want this function to work on the multiple cores that I have on my machine. So this is the way this works. So when I launched this notebook, I have 40 cores. I request 40 cores. So I can do some processing in parallel using the 40 cores in Python. The way of doing this in Python is using the multiprocessing and not the multi-threading. The multi-threading, you will be locked for some details in the language. I will not go into. Multiprocessing is something that will produce whatever. So just really fast going into the standard library. Now, 5 minutes, let's say, and I will be devoting the last half hour to NumPy. And this is the important part. So we collect the language, and I hope if you are not familiar enough with the language, so you take the opportunity to go into the notebook step by step during the afternoon, familiarizing a little bit. The standard library, a lot of those things I will be using the next 2 days. So they should be a little bit familiar for you. What really I need is you to be familiarized with NumPy, how that works. Because tomorrow we will be learning about the NumPy versions of tensor manipulation on TensorFlow, MXNet, PyTorch. So 5 minutes, we relax, and we finish with NumPy. Yes.
So I was trying to understand when you skip this method of quaternions, but like the idea behind those, why? So init is just like the
init is the
initializing.
The constructor, they will initialize the object. Yes.
But like any other function that has like this.
Those are to making. If you see, go down and go down.
Yeah.
And
so I know
there is one place where I'm doing A equal to B or something like this.
Yeah. I noticed that you don't.
So you see.
You don't call them the same way.
A equal to here. Let's get where quaternion with an integer. We are using this underscore EQ underscore.
But how does it understand that?
So the name, the fact that the name is like that, which is like a very specific name, is add, is mold, is EQ, is what is doing the trick. So when you use it with an object of that kind, you can use A equal to this. A plus B, A times B. So all those.
Okay, what is the case of STR?
This TR, it will give you a string representation of the object.
Oh, gotcha.
So what will be the string when you want to print the quaternion in this case, how they should look like? Okay, I would like to be like this, and this. So add multiplication, and this one are I don't remember.
So it was something here or so RF. I'm not sure. Referencing the method, so it's going to be referencing multiplication.
Let me see. I need to check better. I don't want to lie you. So I prefer to say I forgot.
And I want to ask once again, you were referring JSON file here, and I didn't understand like how is it connected? This visualization, is it like those
those are called the Voronoi cells. So they just now you have to that. The idea of the Voronoi cell. The idea of the Voronoi cell is all the points in the surface, in an area. So you see. So imagine we will be working in 2 dimensions. So you have a set of points here. And we want to separate this space in areas that belong to this point, areas that belong to this point, and to this point. So we'll say, okay, the points that belong to this, all the area that belongs to this point are all the points that are closer to this one than to any other point. So you can think here that there is a line here, where all these points here are closer to this one. All these areas here are closer to this one. Here, you can make a line in such a way that all these points here are closer to this one. And you can continue doing this, all this leading goes all the points here. So it will be it's a way of segmenting the space in all the points that are closer to this point than any other point.
So like, but how do we know
So
what is the distance should be? Like, what is this distance should be with all those points? Neighbors? How many neighbors?
You see. Okay, this point. Now you will say your metric. You define a metric. For us, will be, for example, the Euclidean metric. So it will be the position. This one x, y, and this one is x prime, y prime. So okay, what is the distance here? It will be the square root of x minus y, x prime square plus y minus y prime square, and that is the distance. That is my distance. If the distance that I get from this point to this point is lower than the distance that I get from this one or 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 this one, this point belongs to this Voronoi cell. This is the cell associated to this point.
But like, why it was constantly changing?
Because the points are moving. You see, the points are moving.
Yeah. You mean like those
centers are moving.
Okay.
So imagine sometimes in some countries, for example, in the United States, that happens. Sometimes you see things like this. You have one state here where the capital is right here, right? So the cities around here are probably more attached to this capital than they are attached to their own capital, which is probably here. So there is one place where they see, okay, what happens if the capitals of the United States follow the Voronoi rule? So that will be, or how the states in the United States will look like if you use the capitals for using the Voronoi. So that will mean that you will be centering on this capital and searching for all the points that are closer to this capital than any other point. So it will be the Voronoization of the capital. That's the idea. And that is connected with the JSON, because all those maps that you will see in 3D that, by the way, they are used if you go into New York Times, that they see the COVID and all those maps moving around with nice with visualization and dynamics. Those are built on top of those, which is open source. So you can use it for scientific presentation. I used it once. It's really nice for that. D3GS. D3GS. It's something in JavaScript. Okay, so NumPy. I told you, NumPy is the de facto standard for operating with a large amount of numbers. For scientific computing, we are dealing with that. I have one example for you. So you see this immediately. And I will be, let's see, I will be cleaning your kernel. I will be killing my kernel, and so I'm basically cleaning all my space. So I will be getting, okay. So I will be start executing this. So notice that on this notebook, I am only using NumPy and Matplotlib for supporting. But this is, we will be devoting this 30 minutes to NumPy. So NumPy, you traditionally load it like this. NumPy, you don't need to use NP, just the community have used to do it this way. So here I have one example. I have a file. By the way, you can see, well, okay, you cannot see it. I don't want you to see it. But believe me, I have how many? 1 million. So I am making a list of 1 million values. I don't need actually to use the range, but I was trying to play with something a little bit more elaborated. But okay. So we have 1 million values here, another 1 million values here. What happens if I try to make a function using list that computes the product of that? So the product means element by element. So this is the solution. I will be creating, my function will be creating a new list. In this list, I will be running for all, for a range of the same size of the length of the array, and I will be computing the product of A sub I with B sub I, and I will be storing that in the array. So that is my naive way of computing the element by element product with list. I can compute this, and I can try to get a timing on this function. Of course, a computer and a high-end HPC cluster, so it takes a small amount of time. But my point is that with the time it was running a sample of that, in average, you need 98 milliseconds to get this compute for 1 million. And now I will be doing something like that. I will be receiving the two lists. A and B will be a list. But instead of doing that, the looping explicitly, I will be taking the array, the list, convert this into a NumPy array. It's an internal way of storing large amount of numbers. I will be doing exactly the same with B. And in NumPy, with just one command, you can produce the multiplication. It's A times B. A times B is not the vector, the dot product, it's just the element by element product. So that's what I'm doing here. Is my halfway product way of doing the product. Oh, sorry. This is a halfway. And I will be timing. So it's sampling. It's doing this a few times, 100 times. I don't know. Okay, and this is taking a little bit less in average. It's performing a little bit better. What about if we are skipping entirely the list creation? So I am making a NumPy array, A, from the numbers sequence. I am making B, the same numbers in reverse. And now I have just a function that receives two NumPy arrays and produces the product. I will be timing this function. They will be doing it. Same will probably mention, yeah, in this case, they made 7 runs. Okay. So now we lower that to 1 millisecond. So this one is around 500 times better using NumPy. Now, what about if we skip finally this NumPy split it? Because the function is now so simple that doesn't deserve having a function for that. So what about if we just time A times B? Wow, this is so, but the computer is so fast that it made it originally should be a little slower, especially when you are using a slow computer. So I was trying to get, you can try do it, let's say, try to make these numbers a little bit bigger, or a little bit bigger, no, significantly bigger. So 2 millions, 10 million, something like that. Do the experiment. You can do it right now if you're on the notebook. Change this end and re-execute, change the other and re-execute, and test this 4 ways. The list converted into NumPy and make the product, the NumPy arrays with a function, and just skipping the function. It will go into a more and more efficient way. So that is the justification, or that is one way of justifying why we move away from lists, dictionaries, all that stuff. When you are using a Python, a list, every single object, so you have the imaginary memory like this. The different objects sit on completely different places in memory. There is no sequence. There is no way of saying, okay, if I am storing 0, 1, 2, 3, there is no guarantee, and typically it's not what is happening, that the 0 will be next to the 1, and even if we are creating just a list of 0, 1, 2, 3. So this is one thing. This is one of the reasons why this is inefficient. And the second reason is that a 0 is not just a number, it's an object. So they have an extra overload of things in Python to announce the content of a variable in the memory. So this is a Python object. That all those things make things heavier, especially when you are dealing with a large amount of these things, a large amount of numbers. So the solution is something called NumPy. With NumPy, you are working with an entity that is called an ND array. It's a way of storing numbers of the same type. And all the machinery happening for manipulating this, for computing the products, for the matrix multiplication, all this is not happening with Python. It's happening with some other libraries that are well known, that has been developed from the 70s, that are called BLAS and LAPACK. BLAS is the low-level linear algebra stuff. So make vector product, vector times matrix plus vector, things like that. So those are BLAS. And LAPACK is, for example, taking a matrix and separate that in a upper triangular, a lower triangular, getting a matrix, inverting the matrix, getting the eigenvalues, eigenvectors, all that a little bit more heavier linear algebra stuff. The compositions, eigenvalues, eigenvectors, those are. And those are called by NumPy when you need to do operations with those arrays. So that is the origin of the efficiency of that. What I have here. Okay, so a little bit like that, what happens with those, the matrix multiplication. Okay, so just to see how they perform differently when you start using NumPy arrays instead of that. NumPy, from the context of deep learning, NumPy arrays only have one handicap, is that they only live in CPU RAM, in normal memory. A GPU is, I told you this morning, is a very special device where they have its own memory. It has its own memory. You see, for example, if you get a gaming card, they typically have today 4 to 8 gigabytes of GPU RAM. Even 4 is really good. It's very decent for some games. On a machine like this, on Thorny, we have the RTX 6000. They have 24 gigabytes of GPU RAM, where that is the location where you will be storing, well, all those weights and biases will be stored there. If you're doing molecular dynamics, is where you store all the positions and velocities of all those atoms that you will be using to moving. The forces will be stored there, positions, velocities, all that allow you to propagate them. And those are the 24. And the A100s, they have 40 gigabytes of GPU memory. So that is important when you are working with those devices. And that's the only limitation. That's why you can use NumPy directly for training neural networks if you are using a GPU. So that is the reason why we will be in the 15 minutes that I have a little bit an exposition of why this is important, how we use them, create a slice, and the concept behind that. It's important that you have a little bit more deep understanding what they do. So you can put a list and you can create a NumPy array. That's what we did before. We got lists and we got those converted. It's smart enough so you can take a list of a list and convert it into a NumPy array. So it will be like a rank 2 tensor. They have functions ready to use, like pret-a-porter, for making zeros, making ones, getting arrays. They all have the same number. Okay, they have some functions for stacking arrays. In those cases, an array is something like you will not be able to change the number of elements of an array. You are able to change the content. And when you declare an array, when you are declaring an umpire array, different from a list, you are declaring an array, and this array will be something like 0, let's see, -1, 1, 0, 0. Something like this. You cannot start thinking, oh, well, I would like to put another one here and be the same thing. No, what all that you can do is to create a new NumPy array where you can store here 3 or 4, whatever. So once you create a NumPy array, the number of elements remain unchanged. But you can still stack arrays, and that's what I'm doing here with the V stack. By the way, once you see this, well, no, we will see this. So stacking, so you can stack in different ways, stacking with one axis, the another axis. We will see in the ways of the terminology of this, and random numbers. And we will be using. Remember, someone asked about the initialization of the weights. So typically, they are random. So you skip a little bit symmetries at the very beginning, and that's your starting point for training. Okay, and they have some functions, and I was using some of them for creating, for example, ranges of numbers. So they will actually create the array for numbers in a sequence with a specific jump, for example. And linear space. So that the good thing of linear space is that you can declare the number of elements that you want and how they will be jumping. So I would like numbers from 0 to 10, including both extremes, and I want 8 numbers. So I will be making the right arrangement so you get actually 8 numbers in the middle. So this is the most important thing. So the central part, if you want to understand something really, really good, is this part, the indexing, the slicing, and the striping. So I create this one. This one is something that makes very easy for you to understand this. I am making an array, all numbers from 1 to 12. On purpose, I did it this way, starting from 1, so you don't get confused in a minute. So I can take portions of the array. So I can take this. I can see here. If this is something different. So I'm making an array here. And I put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, notice what I got. 2, 3, 2, 3, yes, 6. Oh, we got this portion. And notice how we did. We took 1, 2, 3. From this one, oh, yes, yes. So from this array, we took the first elements here, the first rows, the first 2 rows. That's why you have here a column 2. So the first 2 rows in this. And we took 1, 2, 3. So we skip this one. We are taking from this one. This is the number 1, 2, and we are not using it. So you are taking this. While we are doing this slice, we are not making a copy of this. We are making an object here that will be referencing this area of memory that usually often is contiguous. So this in memory, it looks like